Hello, everyone. I'm Andrew McCallum, Co-General Chair of AKBC with Samir Singh, and I'm very happy to welcome you to the third International Conference on Automated Knowledge Base Construction. Next slide, please. After a series of increasingly successful workshops, we decided, next slide, to create a new conference because there was too much interest and material to fit into a two-day workshop because we wanted to set our own culture, our own increasingly open reviewing styles, and our own meeting format. Besides many of the other conferences in machine learning and natural language processing and other areas that we've known and loved for so many years, we're getting so big and unwieldy that it was hard to build a tight community and hard to build the kind of welcoming atmosphere that we wanted to bring new fields together. Because another one of our goals is to build diversity, both of backgrounds as well as intellectual diversity. Next slide, please. So we built a conference that aims to straddle all aspects of building knowledge bases, from knowledge representation and reasoning to databases, human computation, machine learning, natural language processing, and the many application areas of knowledge bases. Next slide. We had a first in-person conference in Amherst, Massachusetts, and we strove with this, next slide, to reproduce one of the aspects of the very first AKBC workshop in Grenoble, which was to go for an extended afternoon walk together. Next slide. Which was just a lovely cultural experience. Here we went for a walk in the Alps and had just lovely, both scientific conversation as well as community building conversation. Next slide. Walking amongst these old chateaus and monasteries. Next slide. And having incredible views that I'll never forget. Next slide. In Amherst, we strive to reproduce this, next slide, with a walk at a local, much smaller mountain than we would find in the Alps. Next slide. But nonetheless had great conversations along the way. Next slide. And some views. Next slide. All right, well, of course, for obvious pandemic reasons, last year's AKBC had to be virtual. I'm so pleased that it has continued to grow in spite of that added difficulty. Next slide. And that's still the case today, that we are again virtual, but we have also continued to grow, as you'll hear in a moment. And I'm just so pleased with the community that we're building. Running a virtual conference is no easier than running one that happens in person. So next slide. I think all of us deserve or should give a great thanks to our extensive organizing committee. I already did very little this year. Samir really carried most of the burden as general chair. We're also so pleased to have had Danchi Chen and Jonathan Barant as our program co-chairs. Unsal Choi and Walid Amar were our two workshop chairs. And we have actually significantly more workshop interest this year than last year. It's been a great growth. And Matt Gardner has returned again this year for another year of service as our virtual platform chair and helped us in so many ways. And with that, to tell you more about the program this year, I'll turn things over to Danchi. Thank you, Danchi.
Danchi, your mic is not working. This mic not connected.
Okay, can you hear me?
Yeah, perfect.
Okay, thanks, Andrew. Hi, I'm Danqi Chen. I'm the program co-chair for AKBC this year, together with Jonathan Barrett, who is behind the stage right now. So next, I'm going to give you an overview of the paper submissions and our detailed program. So this year, we have received 71 submissions in total. So after a lot of great work done by our reviewers and area chairs, we finally accepted 33 papers to be presented at the conference. Among the papers, 29 papers are archival papers and 4 are non-archival. We also called for papers in a wide range of areas related to AKBC, including knowledge representation and the semantics web, question answering and reasoning, machine learning, relational AI, computer vision, databases, crowdsourcing, applications, and AI fairness. And all the papers will be presented as a short spotlight talk at the conference, as well as a longer poster set presentation at the end of each day. We also have an additional outstanding paper session on day 3. Just stay tuned for that. This year, we also have 13 extraordinary area chairs from different research fields, and they have helped us tremendously during the paper selection process. For our program, besides the paper presentations, we have a set of amazing invited talks. Today, you will hear talks from Monica Lam, Sujit Ravi, Shiva Reddy, Percy Liang, and Peter Clark. We also have reserved 30 minutes after each block of talks, so you can directly interact with the speakers and ask questions on Gather.town. Please make sure to join us for that. On day 2, you will also hear 4 invited talks presented by Jia Deng, David Sontag, Yolanda Gill, and David Parrick. And on day 3, we have another 4 invited talks from Tim Kraska, Hannah Hajish Erzi, Daphna Shahaf, and Greg Durrett. We also have scheduled a 1-hour social event on day 2 from 9:55 to 11 a.m. Pacific time. We have set up different tables, discussion groups, and all sorts of games on Gather.town. And we hope that you can all come, make friends, and have a great time there. Finally, after the main conference, we have 2 days of workshops this year. On Thursday, we have 3 workshops on conversational agents with structured knowledge, workshop on argumentation knowledge graph, and unstructured and structured KB. On Friday, we have 4 more workshops on common sense reasoning and knowledge bases, personal knowledge graphs, natural language processing for scientific text, and expandable graph-based machine learning.
All right, I'll take over now. So after the workshops, I just kind of wanted to quickly go over our virtual conference format. This is, if you're familiar with Gather.town, some of this will be useful to you, but just to sort of give you a lay of the land. We're going to have one main hub, which has a path to go to the mainstream, which is hopefully how you're looking at this right now. We have social activities scheduled for day 2, and we have chats with speakers and poster sessions all in one giant room where you can go for the day. This is what the main sort of room looks like. If you're there, you should already be looking at the stream. If you're looking at elsewhere, all you need to do is press X in that room, and you should see the window. You have to press play again after that. What I did want to talk about was during that video, if you scroll down that page, you will see this pop-up where it allows you to put your questions. And it's really nice if everybody does that, because other people can vote questions up and questions down. And that way we get to ask the invited speakers questions at the end of their talks, right? So even though we have chats with invited speakers, there's also a Q&A session right after the talk, where you can we're going to pick questions from this and show it to everyone. Here are some other sort of minor Gather.town tips that I think are useful to be thinking about. So especially on the bottom left, there is this set of channels where there are some useful things. One of the most useful things is this calendar icon, where if you click on it, you get to see the schedule for the day, what's next. It's in your local time zone. There's a green line that tells you where you are in the schedule. So this is sort of the easiest way for you to figure out, okay, where is everybody, or what am I supposed to be doing? You can just click on the calendar and you should be able to see what's going on. There's a chat functionality as well, which is kind of nice. You can directly message people. So if you have a question for me, you can find me and chat directly. You can chat with everybody who's nearby around you. You can chat with everybody in the conference. You probably shouldn't be using that too much. And you can sort of, a bunch of chat functionality there. There's also a list of participants where you can see their names, you can see their affiliations. If you bumped into someone, had a good conversation, you can sort of use that participants list to find them and maybe chat with them or whatever. If your friends are somewhere in AKBC conference, you don't know where they are, you can also automatically navigate to them, which is kind of nice. And so, just in terms of AV, the way you control your own mic and video is by sort of hovering over your own profile in the bottom right of the screen. That can be useful if there's background noise and such. What I also want to mention is that you can mute someone else. In this example, I'm muting Danchi, although I would never do that in real life. Like in case there's some background noise, somebody else is disturbing you, you can sort of go and mute that. You can also switch off their videos if you need to. And you can even block people. And then we hope it doesn't come to that, but there is all those options if things get messy. And finally, this is a simple trick. If you're stuck in the middle of a crowd and you're not able to navigate out, you can always just press G to become a ghost, and you can sort of float through people. You can't hear them, they can't hear you for that temporary time, but at least you can get out of the crowds. You can't do this in real life, so Gather.town is a little bit more convenient. I wish I could ghost in real life. Okay, I think that's all we have now. I'm gonna now turn it over to Danchi, who's going to introduce our first invited speaker.
Hi, Monica. Do you want to start sharing? Do you want to start sharing your screen?
I have already.
Okay, great.
I can submit
I'll do that. Okay, I'll do the introduction. So our first invited talk today is from Monica Lam, and it's our great pleasure to have Monica join us today. Monica has been a professor of computer science at Stanford University since 1988, and she is a faculty director of the Stanford Open Virtual Assistant Lab. So Monica is very famous, and she's a co-author of the Dragon book, the definitive text on compiler technology. She's a member of the National Academy of Engineering and an ACM fellow. And she has won numerous paper awards and has published over 150 papers on a wide range of topics, from compilers, computer architecture, operating systems, high-performance computing, and more recently, machine learning and natural language processing. So in the last few years, she has been leading the Genie Open Virtual Assistant project, which aims to advance and democratize voice assistant technology to keep the voice web open and protect the privacy of the consumers. So I believe that she's going to talk more about this project today. So without further ado, Monica, please take it away.
Well, thank you very much, Danchi. So hello everybody, and I'm really excited to be here to tell you about the World Wide Voice Web. This is a term that we have coined just very, very recently. It is to summarize the aspirations of a research project that I have been working on for the last 6 years. There are about 2 billion websites out there today on the World Wide Web. We think that in the future you will be seeing 2 billion voice agents that we can connect to. So voice, this is really exciting. This is the third generation computer interface we are seeing. The first being the keyboard. The second is, of course, the bitmap display and the mouse. And now we finally have voice. This is the human language. The computers are finally learning our language, whereas in the past, we forced people to learn the computer language. So this is really exciting. And when we add voice to the World Wide Web, we get the World Wide Voice Web. But with voice, we are so much more flexible and expressive than what we can do with GUIs in all the tasks that we do. So for example, if you want to access knowledge, I want to get some restaurant, some Spanish restaurants that serves paella and a rating of about like 4.2 and above, and I really need to get to it as quickly as possible. So normally that will require me to go to various different sites like Yelp, and then I have to go check the traffic to figure out the time and so forth. But I can just say it all in one sentence with natural language. I can use natural language for other things like web transactions. We have been in the pandemic, and a lot of people were looking for vaccines earlier in the past. You can say to the computer, book me a vaccine appointment at the nearest Safeway as soon as possible. So it is so much easier than what we are seeing today. You can use voice to control social media and, of course, to control the Internet of Things. So, for example, I can say, suppose I travel a lot, I can say, let my dad monitor my security camera for motion. But of course, I don't want my dad to be watching me all the time. I don't want him to be spying on me. So I want to be able to say when I am not home. You see, these are all the kinds of things that we can do in voice that is really hard, hard to get done on a GUI interface. This is so much more expressive. You can talk about cross-site functions, totally personalized, and of course, with multilinguality, that means universal. So if you look at the World Wide Web, we have a browser. Then what do we have if what do we need to use to access the World Wide voice web? And the answer is the virtual assistant. Where are we today? The most popular assistant is Alexa, and it has a third-party platform. It allows people to enter information about their web service and IoTs and so forth in their third-party platform. And it has been introduced about 7 years ago and has been growing quite nicely. Okay, at this point, there are over 200,000 skills in various languages. So how does this compare to the web in its first 7 years? Well, as it turns out that, as you can see from the curve, from the chart, that the dub grew exponentially. And by year 5, it caught up with what is happening with Alexa, and then the growth of Alexa has kind of tapered off. So why don't we see this explosion in growth? There are 2 main reasons, I think. The first one is that Alexa is a proprietary stack. Well, by the way, besides Alexa, there's also Google Assistant that also has a third-party platform. But these are proprietary. It is open for people to deposit their skills, but it's not open to other assistants. You can only access them through Alexa. Whereas the web, the World Wide Voice Web, should be open and decentralized. Another reason is that there is a lot of open source software that was released with the World Wide Web. So this is what we're working on, open NLP technology, and we're building a virtual assistant, an open source privacy preserving virtual assistant, and it is called Genie. And everything here is open to everybody. Everybody can, other people can be building other assistants given that it is all open. So that's the first thing, is that we need to have it open and decentralized. The second thing is that we have to make dialogue agents as easy to build as websites. Okay, now that is difficult. So we came up with this idea called the idea of pre-trained agents. If you think about a calling center, when they hire a human operator, they first of all have to train the operator, but before long, this human can work on various different tasks. They don't have to stick to a single task. And in the same way, we want to train an agent that can work on multiple tasks, and we want to make these agents open. What do I mean by training it on multiple tasks? So what we have built is a Genie tool chain that ticks. If you give me schemas, I will give you dialogue agents. Okay. So for example, if you give me information about restaurants, like it's a schema and the API, we will automatically generate the data, train an agent, and now you have an agent that talks about restaurants. Okay, so what I show in the slide here is an example of the flow. You request, and then you propose them, and then you continue to negotiate or to discuss with the user what restaurants they want to do. So once you trained it for the schema of restaurants with representative entities, then you can apply this to other restaurants, provided that they give you the schemas and the APIs. So that's example of a pre-trained agent for restaurants. But our tool sets work for any databases and APIs. If you give me hotels, I talk hotels. As you can see here, the conversation is kind of like before, but all the words are substituted with hotel words. And if you give me songs, I play songs, okay? So that's the basic idea. Let me show you the architecture. So we absolutely leverage all the work that has been done on pre-trained language models. However, they are not enough because pre-trained language models are not grounded. So we have to ground them. What does it mean? So we ground them for the data, for the most common actions that we take on computers is database accesses and APIs. So we ground it by taking natural language and translate them directly into database queries so that we can now execute it and get real-time and correct information from the databases directly. We cannot just rely on the pre-trained language models. In the same way with APIs, suppose I say, turn on the light, I have to hook it up to the API that turns on the light. So this is what we have to do, is we have to ground these primitives. And on top of that, as I mentioned before, for transactions, a lot of these transactions have a common dialogue state machine. So we take advantage of that, and then we combine this with the schemas and APIs, and we get to different kinds of agents. So that's the basic architecture. There are two key ideas in our system. The first one is that we observe, when it comes to computer-human interface, we have human on one end and the computer on the other. There are all kinds of things we can say as a human, but the computers are limited. All it can really do is to execute a program. So what we have done is that we have created a new language called ThinkTalk, designed for programming virtual assistants. And whatever this virtual assistant can do, we have a formal constructs for programming it. So it covers everything that a computer can do. And it also executes directly, meaning that when I translate natural language into into ThinkTalk, we can simply execute it and get the result. Okay, so we don't have to interpret it and figure out what we need to do after you translate it into some logical form. So what does ThinkTalk look like? We have defined it for various things. I'm going to show you three. One is queries. For example, I'm looking for a restaurant. That's what the ThinkTalk looks like. It's basically kind of like the core SQL functionality, but ThinkTalk is designed to be translated into from natural language. And we also capture dialogues. As I said, the request is in full executable ThinkTalk, and we also capture the results, and we capture what the agent wants to say, all formally. And then when we take the turns in the dialogue, we accumulate the state to represent what the whole dialogue says. We also have end-user programming constructs. So, for example, this is how we can say, when I leave the house, turn off the lights. And the most important thing is that ThinkTalk is extensible. All of our Genie toolkit is based on grammar. So if you want to extend what the virtual assistant can do, just extend ThinkTalk and all the tools will apply. So that's the first idea. The second idea is that we really cannot afford to annotate data. Alexa has 10,000 employees. We have about 5 PhD students. So, and by the way, annotations are not just expensive, it is also very error prone. So what we do is that we synthesize most of the data. And in order to do a good job, synthesis is always limited. We leverage pre-trained models for natural language knowledge. So what I want to do now is to show you a quick summary of how we synthesize training data. Variety is very, very important, of course. And so this is what we do. So our tool, as we mentioned, take database, the database schemas and representative values, and we generate the training data. So for example, you give me a restaurant schema here. So I look at this attribute. So the attribute here, for example, is cuisines and rating. But there are many, many different ways to refer to the same field. And so we turn to the pre-trained models. We generate little full English sentences, and we use the pre-trained models as a paraphraser to get alternate ways of saying the same thing. And we look at the results and we parse the POS, the parts of speech, and we summarize this. This is very important, and record it. This is very important because suppose I say a restaurant that serves Spanish cuisine, that matches the schema. But if I say a Spanish restaurant, now that is, I didn't even mention the cuisine anywhere, and you have to pick it up. And all this information is in the pre-trained model. We just have to tease it out of there. So we get the annotations on the fields. And the next thing we do is that we use grammars to combine these different fields and create full sentences with all the different combinations. And so, for example, here are the utterances and the corresponding ThinkTalk. And you can see here the ThinkTalk is kind of close to the language. This makes it easy for the semantic parser to work well. So instead of using a canonical, just generating one canonical sentence for every meaning, we actually use a large number of templates to create a lot of variety in the synthetic data set. So we will obviously have to cover all the database operations. We also want to cover the standard variety in the English language. So we take out an English grammar book and we say, oh, there are different kinds of questions like who, when, where. So we create templates of that for them, and they are type-based. And then we add in all the things that have to do with, for example, comparisons. We can talk about longer than, shorter than, later than, earlier than, and so forth. And altogether, we actually generate about 900 templates. This is quite a bit of work, but it is well worth it because we're just doing it once for a language, because all these templates are domain independent. The next thing we do is to get domain paraphrases so that we can learn the terminology for a specific domain. Here, we also turn to the pre-trained models for the paraphrases. And as we mentioned before, we are driving the dialogue generation with an abstract state machine, and we just generate just gobs and gobs of dialogues. And then we use machine translation, and we get to dialogues in many different languages. And this is how we generate a lot of this training data. I don't have the time to go into the details for every one of them, so I'm just going to highlight a few things. Let's talk about the paraphrases. We fine-tuned BART. We fine-tuned BART to make it, behave like a paraphraser. But we have to be very careful because these paraphrases sometimes like to hallucinate. So we have to be careful. So I'm just showing you some examples of the kind of paraphrases that we get. Remember, when we synthesize sentences, they are clunky. So if I generate a sentence like search some cafeteria that have greater star than 3, okay, it's pretty clunky English, but you know what I mean, and do not have smoking, doesn't let people smoke. So it turns out that you take the sentence and send it into the paraphraser, it generates a sentence like search for a restaurant that has more than 3 stars. That sounds good. And doesn't smoke. Now that doesn't, okay? Another example is that find restaurants close to my home, and the paraphraser would say, oh, find restaurants near me. That's correct if I am at home, but that is not good enough for a virtual assistant. Okay, and then you cannot just simply look at the temperature as the next example show, because the temperature 1.2 here is wrong, whereas temperature above and lower are actually working. So what do? What we need to do is to filter the noisy paraphrases, and we employ self-training to do that. So the idea is that first, we train a semantic parser using synthetic data. Okay, synthetic data is easy to get. And then the next thing is that we use the paraphraser to generate a lot of paraphrases, which can be very noisy, as I have shown. So we send the paraphrasers through the semantic parser that we have created, and we get back ThinkTalk. The next thing is that we remove all the paraphrases whose parsers do not match the label. Okay, so only if the semantic parser is correct in parsing that sentence do we throw that paraphrase back into the set of training data. And then we repeat and retrain the next version of a semantic parser, and that's the idea of self-training. And as you see here, we are throwing in things that we already know how to parse, but this is the way for us to expand the set of things that it can parse in a very conservative manner. We really don't want to give it bad samples. So, so there are a lot of details in the paper. Let me just highlight some of the results here. So we ran an experiment where we asked the users for questions. We show them what is the fields in the databases, and I asked them to bring up some, to formulate some questions that use at least 2 fields. Okay, so this is a way for us to get to some of the more long-tail restaurant queries. And as we show here in the slide, Genie actually answers more questions than any of the commercial assistants. And I have also shown you some of the examples here to show you that these long tail questions are very, very reasonable. So the reason why we can get this result is because we do a lot of synthesis, and we see a lot of, we're teaching the assistant, we're teaching the semantic parser compositionality. Well, when we talk about the worldwide voice web, we absolutely have to be multilingual. So suppose I have a parser for restaurants. Can I get to all the different restaurants at, in other languages? As you can see here in this example, we have to be able to handle local entities in the native language. So obviously, we should try to leverage neural machine translation. After all, if you look at Alexa, Google, and the Siri, they have at most 20-ish languages. But whereas the translators, we have seen lots and lots more languages. Marianne has 555, but of course we know that many of them do not have very good quality, but that is going to improve. So a standard thing to do is that we just translate at runtime. You take, say, an Italian utterance, and you go through the neural machine translator, and then you get English, and then you go through the English semantic parser to get ThinkTalk. So that's one route. But what we do instead is that we generate the training data in Italian, and then we use this to train a native semantic parser, an Italian semantic parser. This seems easy, except that we notice, as we mentioned before, we have to handle local entities. So, for example, if I have an English sentence, as I shown here, I'm looking for a burger place near Woodland Pond, and then there's a corresponding ThinkTalk. We want to translate that into, say, Italian with Italian names, the Italian foods and Italian places. And the way we do that here is that first we go through the translation. As you can see here, Woodland Pond as a place is now translated into a description. This is no longer an entity. And so what we need to do is that we go through an alignment. We change the neural machine translator so that we can substitute back in the original entities. And with that, then we can do the parameter substitution on the natural language as well as the ThinkTalk in order to generate training samples to use local entities. And with this, we have run this experiment where we use just synthetic data and add 2% of a few shot data that we manually translate. And that will take you 1 day if you use the professional service. And what we show here is that our approach greatly improves over the soda, and it is about, it's a few percent off from the English translation, the English semantic parser itself. So this is pretty promising. And for dialogues, as we mentioned, we have dialogue state machine, abstract state machines. We combine them with the terminology of a specific domain, and we generate dialogue training data. And so we didn't just build semantic parsers, we also build true active agents. And let me show you what that means. We now have an agent that uses a contextual neurosemantic parser. And what it does is that we have the dialogue so far formally represented as the context, and we use that to interpret the incoming sentence in a contextual semantic parser. And the output is a user state. Because we are using ThinkTalk, we can directly execute that, and we get the answer that the user is requesting. And with that, the answer is given to the agent policy, which decides what to say. We generate the sentence. We also have a formal agent state that also goes into the context of the dialogue, which is then used subsequently to process other future sentences. So we ran this experiment on the multi-WAS. We reannotated about 2% of the data in ThinkTalk. We cannot afford to annotate all of it. And by the way, it is well known that there is a lot of errors in the large multi-WAS training data set. So we basically rely mainly on synthesis, throw in a few shots, which is very important. The reason is that we use a state machine to generate the synthetic training data. But Wizard of Oz dialogues have a lot more transitions that cannot be captured or are not captured by that state machine. So because ThinkTalk is powerful enough to represent like 98% of all the sentences in multi-WAS, we can represent it. And with a few shot samples, we can generalize from the state machines to the Wizard of Oz dialogues. And this is how we can get very decent turn-by-turn accuracy of about 80%. So that's the basic idea behind the pre-trained assistant. We talked about how we take schemas and APIs and create dialogue agents out of that. I want to talk to you quickly about another project that also creates a different kind of pre-trained agents that work on customer support. And with customer support, we ground it in primitives to fill in web forms. And then we train it with form filling instructions. So let me give you a quick overview of what that is. Suppose you want to redeem a gift card. Normally, we would fill out a web form, but there are people who are not tech savvy. They would rather talk to an agent. And by the way, on the same site, they usually have the instructions on how you fill in the web form. We take the instructions, we turn them into agent instructions, and we use that to train a neural network that can understand those agents and translate them into ThinkTalk. In this case, the ThinkTalk are the primitives that push buttons and type in words into the text box. And as a result, we get this pre-trained customer service agent. We just train it once, then it can run on any web service instructions. This agent can read instructions and answer calls immediately. You don't have to retrain it. And our experiment with 80 customer services on the web show that we get an accuracy, 70-ish% accuracy. And in the user study, the majority actually prefer Genie over following the web instructions. So this is very promising, and it is a direction that we should follow, but we have not productized this work. On the other hand, we have productized the other part of the work that I spent more time on earlier, and that is because we got the funding from the Sloan Foundation and Verdant Foundation to turn this into a true usable system. And at this point, we have built a virtual assistant called Genie that performs pretty much all the standard things like setting timers and reminders and so forth. But it also have 4 major pre-trained agents for these categories. IoTs, we are using the standard Meta APIs that are in the Home Assistant, which is an open source project. For music, we are using Spotify. Restaurant is Yelp. News is our partners is Smart News. So our agent is defined on the schemas for these standards. So what it means is that if you have a service, if you can adapt them to the same interfaces, you can use our pre-trained agent to do the conversation agent for your service. Okay. So that's the idea behind pre-trained agents. So what it means here is that if you have a company that wants to adopt the open standard, and if there's a pre-trained agent, you get a basic agent without doing any work other than putting on your website in some well-known URI, okay, the name of the pre-trained agent that you are running, which is, what we have done is all open source. And then you describe how you fulfill the database schemas and APIs. How do you connect to your company's backend? Once you put this information up, then Genie will be able to provide for you a voice interface. And that means that if I know the domain name, I can get to the voice agent. You don't have to enter the voice agent into anybody's proprietary platform. And if I don't know the name, then I go through the standard discovery process using a search engine, and I get to that website, and then I can converse with it. Okay, so this is the basic idea behind the worldwide voice web. So at this point, Genie is running on the Home Assistant local gateway. That means that all the IoT information doesn't have to leave your house. And it is also working on the Baidu smart speaker. We will be releasing it and talking about it in our first workshop on the Worldwide Voice Web on November 10th. This is a workshop that is held in person at Stanford as well as online. You can find out more information on that website. And the online version is open to everybody, so please sign up. And I hope to see you there, because this Worldwide Voice Web project really needs contributions from everybody, and especially people in this audience. Well, thank you for your attention, and I have a few minutes for questions.
Thank you, Monica. Great talk. So there are lots of questions on Slido. So maybe we should just choose several top questions. Okay, so the first question is, there has been some work from Microsoft semantic machines on data flow graphs for representing meaning. Do you have any thoughts on what is a good meaning representation?
So yes, we have given this a lot of thought. And what we have done is to say, let's just expose what the computer can do directly to the semantic parser. Okay, whatever the computer can do, the neural network can just translate into it. I don't have to think up another representation without because we know that it is hard. It is so much easier if you don't come up with an intermediate one that you think is better for the neural network. To some extent, the data flow graph very similar to ThinkTalk, but the ThinkTalk has been extended to do events and access controls, and there are many more things that we can do. And what is most important is that all our tools work off grammar. Okay, so you can even extend ThinkTalk on your own, and you just run the same tool, and you will get an agent for your representation.
Okay, great, thanks. So the next question is, how did you approach training the whole pipeline, knowing that there are errors in the annotations? Did you attempt filtering some errors or limit the maximum update step size? Actually,
the whole point about our work is to minimize the errors in the annotations. Most of the data are synthesized, and they are all perfect. And when we designed the ThinkTalk language, we also designed it so that there is a unique representation for every meaning. Okay, no matter how you say it, it always has the same representation. And so when we annotate the small number of samples by hand, we have to stick to that convention so that you really want to make sure that the parser will always generate the same representation and will be considered correct. The ambiguity is the reason why we have so many errors in the first place in annotations.
Great, thanks. Okay, so yeah, we have time for 1 or 2 questions. So the next question is, each retraining would inevitably introduce some noise to the model. So what's your technique in deciding when to stop the retraining process?
We just use the more standard approach. We haven't done. So what retraining are we referring to? I mean, we are using fine tuning. And we basically use a standard approach to figure out when to stop the process.
Okay, yeah. So the next question is, so when deploying a natural language interface, it seems that the user should actually receive some kind of feedback regarding whether the question was actually parsed or not. Yeah.
Oh, absolutely. So in our definition of the language, we make it explicit which ones are queries and which ones are actions. And anything that is an action, we actually have to confirm before we perform it because of the side effect. Queries, we can just say, here is the answer, and we make sure that you know what question we are answering, and that will cut down the extra confirmation step. But one thing that is very, very important is error recovery, and this is an active research project on our side, because you can't just say I fail. Okay, you still have to continue on. And how do you detect the error, and how do you continue with that conversation is really is really important, and that has to be baked into every virtual assistant in the future.
Okay, maybe we can take on one more question.
Okay.
So do you think there are any advantages to including voice in these modules to prevent any cascading errors or information loss?
So is ASR, whether you combine the ASR with the semantic parsing?
Yeah.
Right now, for our prototype, we are using the Microsoft ASR, which has been very well trained. And there is an opportunity, obviously, when you combine ASR with semantic parsing. However, there is so much work to be done on the back end that we are really not trying to improve with that level of accuracy yet. So we just kind of, all the work just starts with the text, and then we continue. We are much more interested in getting to multilinguality, getting to many more languages than improving the accuracy, say, for English. And when it comes to multilingual, we really, there's so much work that by factoring it, so letting the ASR people worry about ASR and us worrying about semantic parsing is just a practical thing to do.
Okay, let's thank Monica, and we also have an actual 30 minutes to interact with all the speakers today. Thanks, Monica.
Thank you.
Okay, Samir, should I start? Okay. I guess I will just start. So hi, everyone. Welcome to the second talk of our first session in AKBC. And it's my pleasure to introduce Sujit Ravi, who's the founder and CEO of SliceX AI. It's a new startup in stealth mode, so we will have to remain curious for a little bit longer. Sujit did his PhD at USC, working with Kevin and I did really love on decipherment and unsupervised structure prediction problems. And he spent a while at Google. He was a manager there and worked a lot on algorithms for efficient learning and efficient inference. specifically semi-supervised learning and graph-based algorithms like label propagation. And his work is part of Google products, many Google products like Search, Conversational AI, Smart Reply, and recently some work on on-device models and the Internet of Things. He was later a director at Amazon Alexa AI, working on multimodal conversational AI. And he has many awards from SIGDIAL 2019, from KDD 2014, as well as nominations at ACL. So naturally, he will talk about large-scale deep learning with structure today. And I'm very excited to hear his talk. So you can take it away, Sujit.
Thanks, Jonathan. I'm going to go full screen. Let me know if you still see You still see it? Just verbal, because I can't see the slides and StreamYard at the same time.
Yep, it looks good.
Thanks, Jonathan, and thank you to all the organizers. Very excited to be here. And by the way, great job on the conference. I was just looking through the schedule and the lineup of speakers, and also the papers and the workshops. I think very, very impressive. I think you guys, all of you, deserve a big kudos for that. Thank you for inviting me. I'm honored. Good morning, good afternoon, and good evening to all the folks joining from everywhere. And just a little bit of about myself, as Jonathan mentioned. So after spending about 10 plus years in the industry at Google and Amazon, where I helped start teams and build machine learning systems at scale, which you'll hear some about today, that has been by now used by billions of people. I decided to start my own company. This is SliceX AI. So without further ado, if you are interested in looking for exciting opportunities in building next generation AI capabilities, we are hiring. Feel free to reach out. I'll share the link at the end. But today I'm going to be talking about large-scale deep learning with structure. And specifically, just as an overview, first I'll introduce this concept that we've been grappling, both in academia and in the industry, especially for problems at scale and large complexity, on how we can do machine learning at that scale, but by leveraging in very clever ways structured information. And specifically, we're going to introduce a framework of doing ML computing using graph. Then I will show how we extend this to the modern deep learning scenarios, what we call neural structured learning framework, and how this is applied in the plethora of problems in the real world. And finally, I will sort of close by showing you specific challenges and also more recent work on how this is applied to conversational AI, knowledge graph, summarization, and related problems. So first of all, I think there are a number of challenges with data, especially when you're doing learning at scale. And one of the most common ones is that label data. We are so used to, even with the advent of self-supervised learning, etc. When you talk about scaling systems and algorithms and making this work at very, very complex conditions, we still fall short of how we can build these systems from scratch for new problems and actually make it work for a wide variety of settings. So one of the common reasons is that label data is hard to obtain. Everybody knows this. And it's not so much as the number of examples that you're in your annotations are few. It is that as the tasks get more complex, right, it's more time consuming to actually even annotate some of these, and the annotations themselves are kind of incomplete, and of course it's a very costly process. So I'll just tell you that this is not just for language. This is a prevalent problem for computer vision and other scenarios as well, but especially for language, it's quite often ambiguous, especially if you look at conversational settings. There are a number of ways to say different things, and the interpretations can be very hard to parse for a machine, unlike humans. So I'll just cut to the chase and tell you the solution. This is a recipe that we've actually sort of found very, very helpful across the board. And I'll sort of double click on each of them in the following slides. And it's as follows. Especially when you're dealing with really complex problems and at scale, what we have found to work really well is by combining unlabeled data, which is easily available in large quantities, and it doesn't matter what modality you pull those data sources from. Combining that with some minimal supervision, that means like you annotate a few examples, whether it's partially annotated or completely annotated. This is also easy to obtain in small quantities. We're not talking about like, fully supervised setting here. And then the most important ingredient is we can combine these two things by exploiting structure in the data to build really, really robust systems that can perform extremely well and also can generalize to multiple tasks. And the structure, the form of the structure that we're going to exploit is by modeling the data using graphs. And if you look, this is what we're trying to learn from, this sort of combination. And essentially, under the hood, what this allows us to do is solve for ambiguity. That means in the context, especially when you have ambiguous instances, the structure helps us reduce the uncertainty during learning and inference. Data sparsity, both in the representation of the models and also in designing sample efficient learning schemes. And finally, dealing with a range of task complexity. That means whether you are in the language modality, visual or multimodal setting, we can do very nice things, especially and scale it up or down for problems like content generation, image recognition, reasoning over knowledge graphs and structured data, conversational AI setting, whether it's for intent detection or even doing end-to-end dialogue understanding. So this is just remember the recipe that I told you in the previous slide. So this is basically the gist of how we do this. We can swap out things with the latest and greatest transformers and all other statistical models, but these principles still stay the same. And before I go on, like why model using graphs, right? I mean, there are a number of ways to represent structure. So in particular, what we found very useful is that graphs are very natural and easy to specify. Like almost any type of relationships can be specified like as a set of nodes and like a type of relationship between them. Whether you're talking about capturing semantic intent by you look at the figure on the left, basically these nodes basically capture the same semantics, underlying semantics. The lexical variations might be different, but like the underlying semantics capture the same thing. In the middle graph at the bottom, we are capturing visual similarity as a property and then using this for a downstream application. And all the way to social graphs, which are more like, think of interaction graphs. If you have users and so objects, how do they interact with each other? And so these can be captured as like sort of either bipartite graphs or multipartite graphs. Now, the formalism that we've employed, over the years, is to treat these graphs as ML computing engines. And so, in a sense, what graphs are trying to get us is basically capture the structure in the data. And machine learning, I mean, you can swap out this function f with any favorite model that you have, is basically trying to learn a predictive function mapping from some input to some output, right? Now we transform, the first step in our process is typically how we transform the data into a graph. So, all the data, whether it's at the granularity of a sentence, paragraph, document, relationship, KG, object, etc., these are transformed into a graph, a set of nodes and relationships. And the property that we're trying to learn, typically it's a class label, or maybe it could be a complex class label that's a composition of multiple class labels represented as yi here, are annotations on top of the nodes. Now, the beauty of this is that, whether you look at it from all the way the extreme case of supervised learning to all the way to unsupervised or even few-shot learning, we can actually apply the same principles and then design very efficient mechanisms that are very general purpose in terms of like how to do learning and inference over the graph. And so this allows us to go all the way from supervised to unsupervised without changing the formalism too much. For example, one way to look at supervised learning in this case would be to treat traditional NLP methods like where you have sparse features as a bipartite graph where you have instances on one side and you have feature nodes on the other side, and just connecting them, they represent membership. And basically in this setting, you're trying to optimize some loss function that says that, hey, for the labeled nodes, reduce the error in terms of uncertainty that you're going to make between the predictions and the true labels. That means you're going to propagate this information through this bipartite graph and say that, okay, if I predict the xi is a different label, then I get penalized. If not, it gets a zero error. And why would you do this? Because Now, unlike just mapping, like, think of SVMs and traditional statistical models, or even neural networks, you can now add additional edges in this sort of graph that says that, hey, feature X is related to feature Y. You can actually model correlations between instances, between features, and all this sort of, and like add multiple signals, all in very efficient fashion. That means you can actually represent them in a sparse format and still do learning, swap out loss functions like classification, regression, etc. In the unsupervised setting, it's kind of similar, except that now you don't have any labels. What you're trying to learn is a mapping of a function between any given node and its neighborhood. Neighborhood being either the immediate neighborhood or maybe k-hop neighborhood, and that amounts to, in the most common setting, representation learning. So you're trying to learn some function or representation of each node such that the similarity between representations of nodes that are strongly connected are very close to each other. That means the distance is small. Real world example of this looks like as follows. If you want to do, remember the image graph that I showed you as an example earlier, you want to do semi-supervised learning on this graph. You could start with this graph where you can see, intuitively to any human that looks at this, the edges are representing some sort of visual similarity. And just with one labeled example per class, you can actually use this information and the graph structure, propagate it, and learn a labeling on all the nodes in the graph. Now, for example, most of the nodes on the left side are tagged with a high probability as scar concept versus like one on the right is the line. And in some images, you have both of these. So you will actually have a probability, non-trivial probability associated with both these concepts. Now, this is the general principle, right? So, but of course, to get to that, there are a few steps. So especially in the large scale setting. And so we break it down into two basic steps. Like one is going from the data to the graph modeling. That means you're constructing a multi-graph, and then the graph learning. So if you're interested in a little bit more detail about some of this stuff, like please check out the AI 2016 work where we introduce how we model this. Essentially, it allows us to like define a framework which scales to hundreds of billions of nodes, trillions of edges, and even billions of label types. That means think about your prediction problem being like not just 100-way or 1,000-way classification, it's like over billions of labels. And especially for language, this is important because the labels can grow exponentially if you have composition of labels, right? For example, this sentence belongs to concept A and B, right? So you have these conjunctive concepts. The data, as I mentioned, can come from different sources. Like it could be text, like words, documents, conversations, or it could be visual, like images or videos, or speech, spectrograms, entities, product attributes, what have you, or a combination of these. Now, it is like, so just to caveat it, it's the first challenge is actually generating the graph for large data. That is a non-trivial problem. You don't want to spend most of the time in like sort of, scanning through your whole data and then actually trying to generate a graph for that. So we have very efficient and approximate algorithms to actually do this in linear and sublinear time. So the original paper and some of the follow-up papers talk about this. So essentially, you could do sort of a single sweep of the data and generate a graph that captures similarity with some provable guarantees. So that now gives you a graph over your entire data set. And the nodes represent the objects, text, image, or speech. Edges capture the pairwise relationship. Now, take an example here. This is basically, imagine you have an application in the conversational setting and you want to learn about emotional concepts. Or, more recently, you want to actually annotate your comments or social media with the toxic labels, toxicity, detect toxicity. So you could just start with, on the left side, simple words like, awesome, ROTFL, etc., and take dense and continuous representations like your favorite model, whether it's BERT or, previously Glove, etc. Take the embeddings, and then we can convert that to a similarity graph where we say that, hey, the middle image basically shows you how certain words are connected to each other. With thicker, the thicker the edge, that means the stronger it's connected to, like for example, awesome to great. And then I can label a single node in this graph. Like, for example, I say, I have no idea about, what all the different instantiations of the concept funny is, but I know laugh corresponds to funny. So I label laugh as the funny concept. I can propagate this information and then learn that ROTFL, even though I don't know what it means, is associated with the same concept. So this is, in general, the principle. And this is, if you're interested in emotion and like going deeper into this topic, we have some work with folks from Stanford, on how we generate like a really large emotion data set using a number of methods. This is Dora and Dan Juravsky's group. Please check it out. But essentially, that can be scaled up. Of course, to make it work, there are a number of challenges. First of all, to process, as I said, once you generate the graph, you need to actually do inference over the graph during training and also, sort of real time. And for that, there are two basic ideas that we introduced. One is like we can do distributed graph processing. That means we don't obviously sort of have to store the entire graph in memory or on a single machine. We can distribute the computation over the graph. And the second is most of the objective functions that we define over the graph in terms of learning, whether it's to do classification, regression, or even sort of structured prediction, boil down to defining a loss function. And the learning translates to doing some sort of a gradient update iteratively in every step. And what that means is in every single iteration, you're now actually taking every single node in the graph, or maybe a subset of the nodes in the graph, computing its gradient update based on its neighborhood. And like you have some sufficient statistics that are passed from its neighborhood to that node, and you aggregate it, and then you sort of propagate this information out. The hardness here is that, if you have a really complex, prediction problem, that means your number of labels, for example, is 100-way. And suddenly you want to now make a prediction over 100,000 concepts or 1 million concepts. You now have to keep sufficient statistics for all these labels, per node, and that actually can be prohibitively large. So what we introduced here was a streaming approximation algorithm that guarantees that every time you're doing the gradient update, even though you have let's say, a really large prediction problem, like a 1 million-way classification problem, you're still maintaining constant memory per node. And that allows us to scale from, let's say, whether you do 10-way or 100-way or a billion-way classification, you get the same computational complexities, you very efficiently scaling. And it is provable under certain conditions. That means you're not losing out in terms of like the probability or sufficient statistics beyond certain factor. So that is important, especially if you want to get really high quality systems and also keep the computation under bounded terms. Next, switching so this applies to, you can take any statistical model and apply it to this framework. What we did is like, okay, how do we extend this to deep learning frameworks, right? And recall the graph that I showed you earlier, or the image that I showed you earlier. So graphs, on the one hand, give you, structure and very nice way of, or an efficient way of capturing the structure. ML models, including deep networks, are good predictive functions. Deep networks are, in particular, a very good predictor, right? Compared to some of the older models. So there are different ways of combining this, right? You can go left to right, right to left. But before I get to, how that, sort of manifests, right? So some of the real world applications where we've been really, really successful in applying this idea of combining graphs and neural networks, what we call neural structured learning, stem all the way from your daily applications, like, for example, Smart Reply, which we introduced. This is now used as a core like feature in every single email and chat application. So this is basically doing automatic response prediction based on the context. And all the way from that to your like email classification, how do you group emails based on the topics into like labels and organized folders, to image recognition, doing state-of-the-art image recognition on like millions of concepts, and even doing more complex tasks like video summarization. How do you translate a whole video and create a 10 or 20 second summary of this? This is our ICML paper from 2016. And combining these into multimodal experiences, like you have conversational, sort of understanding that you got to do. You have to also do reasoning over images and also text. And generate the right response at the right time, both based on the visual and the sort of language input. So this is like, if you're interested, you can check out the Dub 2018 paper. All of these have one thing in common. These are real world applications of neural structured learning, sort of working in practice at scale. So I'll just now, sort of share how some of these are, like the algorithmic components work for some of these applications, right? So as I said, the challenge is not, most people think for like content generation, etc., whether these are RNNs or transform models, it's like you give like simple input output examples, like, millions of examples of conversations, and you now have a model that, sort of starts spitting out things, right? Including all the way to the latest and greatest, large language models. Unfortunately, when you want to do this at like beyond a certain scale, you really need to have controllable knobs, and to ground it in sort of specific structured objects, or even instances that you really can, like a human can understand and reason over, right? To avoid going haywire, but also to generate something that is meaningful and usable. The usability and the explainability are super important when you're actually working with real world applications. So in the case of Smart Reply, what we did was like combine graph learning and sequence model. And the way we did it was, the graph structure, basically the graph learning, helped us map all possible messages, from what we sort of did inference over into a structured space. That means there are, let's say, 1,000 different ways of saying thank you, or 500 different ways of expressing gratitude in typical conversations. All that is mapped into a structured object with interconnections. And then you have a neural network that looks at the structure, is actually taking the structure and the input message as input. And then based on the context, it's actually predicting the right relevant response. And why this is important, one of the benefits is like shown in this slide here. Like, for example, if I say, can you join tomorrow's meeting? I think there are countless papers that have, been published over the last few years on dealing with how to sort of suppress the ability of neural networks to sort of generate and return responses that look very similar to each other, right? Number of ways to incorporate diversity in responses. But this is one area that like the structure actually benefits and gives you a natural mechanism to do so. For example, if these are all the possible responses that, that are valid for this input message, but, just showing you the top 3 or 4 is actually in many cases useless, because if I say, sure, I'll be there, you already know what that means. You don't need to say it like 5 different times, right? You have constrained space. We can surely probably 3 or 5 responses is best. So the structure allows us to sort of collapse these and say that, okay, now I'm going to, if I said, sure, I'll be there, now I'm not going to, sample from any of those responses. Instead, I will actually show you a response from a different response cluster, which is like, sorry, I won't be able to make it. So these diversity in their learned semantic intents can be automatically sort of infused into the network. Switching from language, the concept and the idea stays the same for large-scale, semi-supervised learning over images. So, the original inception models, which were sort of, first surpassed the human level accuracy on ImageNet type problems. What you've seen, you probably don't know, but like have seen over the last few generations, is the image recognition models, like from Google and the other players in the industry, getting better and better. And what our group is responsible for is like, how do you scale this to do recognition, not just for thousands or hundreds of thousands of concepts, but millions of concepts at the same accuracy. And this is where there might be a misconception that the companies would have like a lot of annotators, but if even a company like Google, if you had to sort of like build a supervised system or even a semi-supervised system with and require annotations of that quality to over the data sets that we really want to make predictions over, it would take us like 10 or 15 years or something like that. So the reason we are able to do this in at very high quality and also get robust systems is because we have this sort of structured learning under the hood that is actually constantly sort of interacting with the deep learning system, and then together they become like very efficient recognition or predictor machines that can then scale easily, both in terms of data and also in terms of the complexity of the concepts. So, about the time that we sort of started publishing work on this and also deploying these to real world applications, the obvious question, anyone who saw the previous sort of slides would be like, okay, you have graph learning and you have deep networks, right? I mean, and it seems like you're doing some sort of optimization in both spaces. Why can't you do sort of joint optimization, right? I mean, really any ML person, the joint optimization come naturally to us. It's very difficult to do this at large scale, and also especially to make the learning and inference work. So our stab at this is what we call neural graph machines, and these are precursor to the graph neural networks. If there's a whole field of graph neural networks now, so GCNs, etc. These are what we found very efficient mechanisms of doing neural structured learning, doing the joint optimization and also making it generalizable. And the principle is simple. What we do is we treat the neural network optimization just like we would do for any other problems, except that instead of feeding it instances, we would also feed it the graph structures. And the joint framework basically decomposes the objective function on what we are trying to optimize into two components. The first one is the neural network. That means how do you take the input, for example, an image, and then pass it all the way, do the forward propagation, and make a prediction whether it's a cat or a dog, right? And then back propagate the error in terms of gradient update. The second component is over the graph. That means what we try to do is we also enforce that the networks, the instances that are passed to the neural network, they also satisfy some properties such that there's a MathCalD thing that you see here. It's not important. You can check the paper for details. Enforces that nodes that are strongly connected in the graph that is provided as input are sort of forced within the neural network layers to actually have similar representation. Now, the nice part about this is if you decompose the objective function this way, you can generalize to a plethora of objective functions, loss functions, and also go from supervised learning to semi-supervised learning to unsupervised learning in a very nice fashion without changing anything. So it allows us to do end-to-end learning using back propagation like you would do typically with other networks, like stochastic gradient descent or any other sort of optimization method. The other bit is that it doesn't depend on the structure of your network. For example, if you remember the original graph convolution networks, I mean, the reason why, the convolution operators were applied only one hop or two hop is because of the complexity. Like in this case, we don't encounter that. These are sort of decomposed over sort of individual subgradient updates, and whether we swap the network with the feed forward or a convolution or an RNN or a transformer, the same principles apply. So you can swap out your network architecture with a new one and then still have the same kind of benefits and leverage it using the graph structure. So naturally, because of the extensibility, you can apply to a variety of problems. But one of the most important things that we found with this was that the NGM type models yield smaller and faster networks. So they're very sample efficient. So what the structure is buying you is if you had a 9-layer network, you could achieve the same accuracy with a 4-layer or a 5-layer network and get the same quality. So this is super important. Basically, that's sort of reinforcing this sort of idea that you can become more sample efficient and leverage all the benefits using the structure if leveraged correctly, right? So this is, if you're interested in neural structured learning, this is available in TensorFlow open source. So it's been used by a number of companies and academic research labs. Feel free to ping me if you have more questions on this. We've applied this to this sort of framework to image representation learning. And a different idea, but in the same kind of related note, is you can even go beyond language problems and visual problems and do things like graph partitioning, which is a fundamental algorithmic problem. And you can actually use this structured learning, neural structured learning idea to learn good graph partitioning frameworks. To check out the ICLR 2019 paper for more details on this. Finally, in the last few minutes, I'll just switch gears and say that, beyond doing the things at large scale, and also for the applications that I showed. This is AKBC. This sort of framework is very, very relevant for doing reasoning over knowledge graphs. So there are a number of applications for like knowledge graphs, like question answering, multi-hop reasoning, etc. So there are two different works that we introduced recently in the in 2019 and 2020. This is with the first one with Prabhat, one of my interns, and Andrew McCallum from UMass, and the other one was from Innis and Chris Ray from Stanford. Both of these basically are ideas on how to address reasoning or do multi-hop reasoning over this knowledge graph structures by like different types of graph attention mechanisms. And the first one is basically trying to do this over like, doing link prediction, like, and even like, fact completion, right? Oprah Winfrey nationality, and you want to identify the answer. It's not obviously given within one hop. So that's why you have to look at the entire graph. And the idea is that instead of treating embeddings or representation of nodes as static, you would actually do multi-hops and dynamically generate contextually relevant embeddings. That's why it's called attend to neighbors and using the neighborhood. And that gives you a much better function for pulling out the right answer from the entire set of nodes in the subgraph. So this leads to state-of-the-art performance. And for the second concept, in the interest of time, please check out the ACL 2019 paper if you're interested in the first one. The second one is what happens if you want to learn relationships, but that are not symmetric. And we introduced the first work on hyperbolic graph attention mechanisms. So basically what it allows us to do is learn these hierarchical and logical patterns using this novel, hyperbolic graph attention mechanism. And the idea is that you can do these things with traditional embedding-based methods, Euclidean methods. Unfortunately, it requires you to increase your dimensionality. You need, let's say, 1,000-dimensional vectors to capture the same complexity as you would do with, say, 100 or 50-dimensional vectors and using hyperbolic operations. You can check out the paper. This is from ACL 2020. It's a very interesting work. And finally, last but not least, there's more recent work on how do you use graph structures to do things like multi-document summarization. So here, the setting is you're doing question answering, and the graph appears not just within the document, but also across documents. Documents are related, but also concepts within the documents are related by sort of relationship types. And so this is work from NACL 2021, and it seems like if you were to be cleverly encode the graph relationships and actually pass it to your text encoder and combine with a bot style model, you can actually achieve state-of-the-art performance for complex tasks like abstractive summarization. So with that, I'll stop. Thank you once again for the time. And as I said, we are hiring. So if you're interested, please feel free to reach out, and I can take some questions.
Okay, you can hear me now, right? So thank you for this great talk. We're a little bit over time, so we'll take a couple of questions, and I encourage everyone to chat with Sujit in the chats and posters. So let's just take a couple. So the first question, it's on screen. Do you have any thoughts on how to combine large pre-trained models and graph structures, and would memory become a challenge in this case?
Yeah, it's a good question. I think, but we've been sort of facing this, like in the series of works that I showed earlier. You can use the large pre-trained models in two different ways. Either you can use it to generate the representations that would go into forming the graph structure. That means you would use the representations to define some sort of similarity metric over different sort of instances and then create the graph structure. Then you can use a simpler model to do the inference on top of the graph structure. Alternatively, you could actually define the update function that you're doing within the node during the learning using the pre-trained graph model. Pre-trained language models. There, the memory becomes the constraint, right? So you would potentially have to store the large language model within that node, right? The machine on which the node is. But again, there are mechanisms to sort of deal with that. You can split this over different machines and access parts of the language model, the parameters that are most relevant for that node, etc. There's systems level things you can do to make it faster. Split this over different machines and access parts of the language model, the parameters that are most relevant for that node.
There's some replay.
Split this over different machines and access parts of the Okay,
It
I guess
stopped.
it was important. That's why I play back twice. Okay.
Okay. Maybe one last question. So you mentioned, you mentioned that you have a neural network that takes a sentence and a graph as input. Isn't the graph too large? Is there some retrieval component over the graph before it is being fed to the neural network?
Yeah, this is a great question. So you don't store the full graph ever, when you're actually reading the input. So we actually decompose the graph into edges. And what we do is, just like how you do batch processing over nodes instances, you would actually do batch processing over edges. So that's the difference. And so the neural structured learning framework, the TensorFlow that I pointed to, basically reads in these edges and sort of like constructs batches out of them. So now, in every iteration, you're only sort of computing gradients over the batches.
Great. So we're out of time. I really ask everyone who asked a question and we didn't get a chance to ask it to the chats and posters. And I'll hand it over to Danchi now, if Samir will aid us. Thank you, Sujit, so much.
Okay, so our next invited speaker is Shiva Reddy. So Shiva is an assistant professor in the School of Computer Science and Linguistics at McGill University. He's also a Facebook CFAR AI chair. Before McGill, he was a postdoc researcher at Stanford University. Shiva received his PhD from the University of Edinburgh in 2017, where he was a Google PhD fellow. Shiva's research focused on representation learning for language that facilitates systematic generalization and conversational models. So Shiva has done a lot of influential work in semantic parsing, question answering, and related topics. So on a personal note, Shiva and I have worked together in the past on conversational question answering. So I'm very excited to hear what he's going to tell us today. So without further ado, Shiva, please take it away.
Thanks, Danchi. Can you hear me?
Yeah.
Oh, yeah. Great. Thanks for the very nice introduction, and hi, everyone. AKBC is always very close to my heart. This is my fourth AKBC. I think I missed one AKBC in person, but yeah, hopefully I will be able to attend more in-person events in the future. But for now, very happy to meet all of you. So today I'll be talking mainly about two projects, specific projects, and I will talk about some of the challenges that we have to solve before claiming that language models can do a lot of things. Okay, so just as we all know, we have to talk about the elephants in the room, and the elephants are the big language models, and everybody knows about GPT-3 now. It's 175 billion. But if you think about why these models are working, two main things come to my mind. So one is they have extremely good generalization ability, which means that even if you haven't told these models what syntax is or what semantics is, they do tend to learn and generalize to many sentences. And the other good feature, which is also very important, is memorization. So they tend to remember world knowledge, also some task-specific knowledge that is important to accomplish the task. So these two things are very important, and they have to work with each other. If one of them is it's good on one side, then there'll be problems. So it's like a yin-yang relationship. And if you think about what people have been doing with the language models, and they have been using language models in two ways. So one is for direct querying. I mean, it's every day you come to realize that the language modeling has a new ability. Like one of my recent thing is prompts, and I'm extremely impressed with prompts. But for this community, what is really important is that they can actually act as knowledge bases. So if you take this sentence like the capital of Canada is blank, a pre-trained language model can give you it as Ottawa. It's better than me because initially I was thinking Toronto, but it's not Toronto. So people have shown that these models are very good at that. Like if you see bird, this red curve represents bird precision at 1. If you the first prediction, it's around the mean precision at 1 is 30, and if you have the model predict more, the accuracy increases. So it's very impressive that these models can predict knowledge. But we should also remember that these models have several drawbacks. One of them is even with a slight change in distribution, the models fail dramatically. So this is one example. So, if you take macOS is developed by blank, and the models will predict it as Apple, Microsoft. So the first prediction is Apple, and which is what we care about in this case. Let's do something like this. macOS is not developed by, and the model still predicts as Apple, and this is not something we want. So the model successfully memorized the knowledge, but because it has never seen macOS is not developed by, it has a lot of problem. It's still generalizing the seen thing to this unseen thing. Okay, so this is one problem. And let's look at the other use case. What people use language models for is one of the main aspects is transfer learning. So you have models like BERT, where you fine tune on your target task and measure in-domain performance. And it has shown to be extremely powerful, like Squad. If you take Squad, we know that before transfer learning, we were on the high 70s, but after transfer learning, we are above 90s, right? Very impressive. But again, if you actually test these models in out of distribution setting, even with a slight change, they have dramatical results. So what do I mean by out of distribution? So let's say you take a language model, fine tune it for natural questions. I will briefly describe what is natural questions in a while, but then the questions contain, it's a passage retrieval task where you have questions from Wikipedia, people frequently asked questions by people on internet. And if you see, it's because the target documents in natural questions are Wikipedia. So these are mainly some Wikipedia questions. When are hops added to brewing process? What does word? So let's say we train this model, and now we want to test it in a completely different setting, which is like change in domain. We are not going to retrain. We're just going to use the same model and see what it does. So here I want to test it on machine learning questions domain. So where well, the examples look very different. What is supervised learning example? How do you compute vectors in word to vector? And you see that the language is very different, right? And if you see the domain generation performance, it's actually disappointing. All these models, if you take the task of passage retrieval, retrieval at one, this is also precision at one, you can call it. So that one, it's around 10 points for machine learning questions, whereas on natural questions, it's around 60. I'm sure there are better models now. For question generation, it's also the same story. They work very well for natural questions because that's what they learned. But when you test it on out of distribution, they completely fail. So here you get a Rouge score. Let's say here you get 10, 12 points or 13 points drop in performance. So in this talk, I want to solve these problems. I mean, it's always a big word, but at least show two methods to how we can attack this problem. So here we are developing a model called BERT-NOT, where it still predicts meaningful things and factually correct. macOS is not developed by. What we want is Microsoft, things like IBM. This is, if you talk about AGI, you can say itself. The other one I want to talk about is a new technique that we are proposing, which is called back training. And this is, we are focusing on unsupervised domain adaptation. One of the popular techniques for domain adaptation is self-training. And if you see the results and the end results, we get our back training achieves much better generalization performance. Okay, yeah, let's talk about first work. This is a work from Aryan Husseini. He's a PhD student of Aaron Corwell, and yeah, I was lucky to collaborate on this project. So let's talk about the basics of language modeling. How are we training language models in the first place? So it's all about maximizing the likelihood of predicting a correct token, right? So if you take this sentence, the movie is very blank, and that's and you want to predict what that blank is. And from the large unsupervised data, you are trying to predict, okay, boring is one of the possible predictions. And the model learns to maximize that probability, and in the end, we would have a language model. All of this is good. But one of the things that you should think about is that these language models are making use of mainly positive examples, There's not much work on making use of negative examples, and this is where you could also use negative examples. Noji and Takumura showed that you can also use negative examples. So, for example, let's say you want to learn a bird with better syntax. How can we do that? So the keys to the cabinet are on the table. In the likelihood training, you're trying to say, okay, this R is correct. If I mask this, I want to predict R. But in the negative case, the keys to the cabinet is on the table. You do not know what the correct instantiation is, assuming. So we know that is wrong, but we don't know what the correct one is. So what we want is to maximize the probability of not predicting is, right? So that's called unlikelihood training. It's very simple. It's just like 1 minus probability of a likelihood prediction. Okay, yeah. So let's go and see whether this works for. So this works very well for syntax, but what about semantics? And if we want to teach the concept of negation, okay, what I'm going to do is okay, I'm going to sample negative sentences. So let's say the movie is not, and in the corpus I have boring. I want to maximize this unlikelihood probability of, and the goal is not to predict boring here. But it doesn't make sense because we do want to predict boring, right? It's syntactically meaningful. And let's say you apply unlikelihood training here. What will happen? What will happen is that you would you would have catastrophic consequences on syntactic abilities. The model will start predicting the movie is not the movie is but. It's syntactically invalid sentence. So how can we fixing this in semantic space is much harder. So then we came up with this idea that okay, why don't we teach these models? If something is true, what can we say what can we say more about that sentence? So if sentence A is true, what can we tell about sentence B? So here we came up with this objective or a data augmentation method where we take a true sentence. Given that sentence is true, so the movie is boring. I mean, in this context, we assume that it is true. What can we tell? The movie is not. We can definitely tell the movie is not boring, right? So we can actually apply unlikelihood objective here. So we want to maximize this unlikelihood probability. And if you check the output predictions, they are very interesting. So if you see the movie is boring, so the model did not lose its syntactic abilities. The movie is not, so because it doesn't have a reference, so the movie is not boring is a perfectly valid sentence. But if you take this iPhone is developed by, the model has to memorize this example, right? So there's only one person that developed iPhone. So the model memorized this fact. And now we are telling the model not to predict something there. So what it does is it starts predicting for factual sentences in the real world, it starts predicting gibberish. Again, so iPhone is not developed by and that's what. The reason is that Apple is very similar to other companies. So it starts taking shortcuts. So how can we fix this? So what we did is, we applied the distillation procedure here so that the model doesn't forget what is also meaningful. So again, going back, if you tell the sentence, the movie is boring, you can still say the movie is blank. The movie is boring, right? It's still boring. So we applied distillation here. So for negation, we applied unlikelihood, but for not negation, just for normal sentences, we applied we want to minimize the difference between the previous bird predictions and whatever we are learning, right? And if you see the predictions, yeah, this is exactly what we want. If you take iPhone is not developed by, and the model starts predicting Microsoft. So we are telling that all the predictions of bird are correct. So try to retain that, but maybe in the unlikelihood one, you're not trying to tell the model, okay, don't predict Apple. Okay, yeah. So if this is the entire setup. We randomly sample sentences from corpus, so they don't have to be factual. So we randomly sample, and once we sample that, we assume that it is true. Given that is true, we will apply unlikelihood training. So this method is very generic. Okay. So in this case, we are applying it as admin. I just want to check the time. Okay, yeah, I'm doing good. Okay, so how do you evaluate this model? So we will go back and use the standard techniques where language models have been probed for their factual knowledge. So which is like llama probe, and then there's also negated version which is called negated llama probe. Okay, so the idea is you have Bailey Peninsula is located in and blank, and the answer is Antarctica. And here you want to predict anything else other than Antarctica. Ideally, you might want to predict continents. But that is not what this test checks for. So we have to evaluate whether it predicts meaningful things or not in a separate task. But here we want to test whether the model predicts factually correct statements or not. And here these data sets are created from things like Google graph, knowledge graph, um, also Wikipedia, ConceptNet, Squad, different things. And if you see here, so this is on llama language models as knowledge bases. So if you take BERT, what we want is precision at 1 to be very high. And BERT, if you see on Squad, it's doing 13, concept and so on. It's getting some numbers. And let's see what BERT does. So impressively, like BERT does not forget things, factual facts. So for statements which does not include negation, it still predicts correct stuff. So there's no catastrophic forgetting here. And let's go to sentences which has negation. So now you don't want to predict Antarctica there. You want to predict something else, right? So if you take BERT, the lower the score, the better it is. So this is, we are talking about precision at 1, and you can think of this as error rate. So the lower it is, the better it is, right? So if you see here, BERT does understand some concept of negation, not fully, but to some extent it does have some concept of negation. And if you go to BERT not, you see that it almost goes to 0 on some data sets. So we do believe that BERT not understands the concept of negation. It almost we see drop in every data set. Okay, so this is for knowledge graph. But you might ask, okay, let's see some outputs, and then we can see what about the other. So like, is the model predicting meaningful things? So the question, right? So if you take iOS is developed by, and these are the predictions of BERT, Apple, Google, Microsoft. Apple, we care about Apple. It's good that it's predicting Apple on the top, and also the same. BERT not is also predicting Apple in the top. Whereas if you take iOS is not developed by, BERT still predicts Apple on the top. The distribution has not changed much. If you see here, it's almost entirely the same. Whereas BERT not, Apple actually went down, and the top prediction is Microsoft. And it's interesting that it did not lose also the syntactic ability. It did not predict words like the or but, right? And if you take another thing, the majority of Amazon forest is in Brazil, and you don't see in BERT not, the majority of Amazon forest is not in, you do not see Brazil at all in its predictions. The same, we tested on a lot of things, so you see that it's actually meaningful. This is an interesting sentence. Charles Nodier died in Paris, and the model did not pick cities here. It actually picked something meaningful, but not cities. We don't know why exactly. Charles Nodier did not die in vain, did not die in error. Okay. We also wanted to see what other abilities did the model forget or retains, and so what we tested it on SNLI and all the standard natural language inference benchmarks, and we do see that BERT is doing very well on sentences that do not have negation. You see that it's you have 89, but with negation it drops a lot. So our model does perform better than BERT. It's not perfect. You still see that with negation, it's still there's a lot of improvement that we can go for, but it's better than BERT. Okay, yeah. So this is how we can improve the linguistic ability of BERT with unlikelihood and with reference for negation understanding. And we saw that it does work very well for factual predictions, and also we saw that it generalizes to natural language inference. You can check out the code base here. Okay, I'm going to switch gears now and talk about other thing, which is transfer learning. Okay, so we already covered generalization. So this is, you can think of this as generalization. Now we are going also for transfer learning. Here we want to test it on unsupervised domain adaptation, and this is my graduate student Devang, who did this work with collaboration with with Corbit, which is startup, which is like Coursera, but it has agents instead of tutors, human tutors. Okay, so in transfer learning, just to recap again, we have BERT and we fine tune for a given task, and we know that it works very well in distribution. So we already know that it performs very well in squad. But what happens when you take the same model and test it on unseen domains? And that's where we see incredible drop in performances. I also encourage you to check out our work in 2020 in Europe, which tells that no matter what you do, these models, they are not going to generalize, unfortunately. So this is so no matter if it is GPT-3 or any of these, we found that there are limitations in the architecture itself. But like keeping aside the limitations of architecture, we are trying to see, okay, with the existing architectures, what can we do, right? So if you take natural questions, you fine tune for natural questions and test it on natural questions. It works very well. But if you test it for machine learning questions, the different domain, we saw that it drops a lot. This green is the drop. You can see that it drops for both question generation and for passage retrieval. Okay, so just a brief background about natural questions again. So these are real search engine queries, and the target answer for these questions, the target answers are, we will assume that they are in Wikipedia. So that's how natural questions assumes. Okay, and they filtered out questions that do not have answers in Wikipedia. So the question is, when are hops added to the brewing process? And the answer is after mashing the beer, what is boiled with hops, and so on. So these are the nature of questions is like mostly frequently asked questions, what people care about. So there is no data set for machine learning questions, and so we went ahead and collected a data set where you can test your models in unsupervised domain setting. So like collecting label data is very hard, as Sujit also mentioned, and also Monica mentioned in her talk, like collecting label data is extremely hard. So we went ahead and collected some label data, but we want to use this label data as our test set and not to train. Okay. And so this is how our data looks like. What is the difference between eager learning and lazy learning? And you see the eager learning, this paragraph definitely answers this question. And this is again from Wikipedia, but we are focusing on the machine learning aspects. Okay, and one of the most important things to remember is people are trying to learn stuff, so they don't tend to ask very generic questions. They tend to ask somewhat specific questions. So if you take this paragraph, what is eager learning is the easiest question that you could ask. But most people, when they're learning stuff, they might already know something about eager learning, and they want to know more about what is the difference between eager learning and lazy learning. So the questions are mostly of this nature. So if you go and look at distribution, this is the distribution that we care about. So if you see in machine learning questions, you have description questions. So what, the questions that's kind of what, when, who, where. And you see natural questions, you have 86%. So mostly these are very generic questions, whereas machine learning questions, you just have 39%. And there's a large portion of questions that have things like how do we compute word vectors? And there's just like the really minimal percentage in natural questions. So the distribution is very different, and you see why these models are not generalizing, right? And yeah, there are a lot of other questions, explanation, comparison, preference. Okay, I also want to tell you that there are lots of ways in which you can collect a lot of unsupervised data for a given domain. So you can, if you talk about machine learning, you can go to a machine learning textbook or Wikipedia pages of machine learning. I mean, you have millions of passages from textbooks, so you do have unsupervised data, and you do have a lot of also real questions that students asked, like from Stack Exchange. But we do not know their pairings. We do know, okay, you have passages, you have questions. We do not have these pairings. So can we exploit this unsupervised data to build better models that generalize to this machine learning domain that we care about? So one of the popular approaches for that is self-training. As you may know, in self-training, what you would do is you have some source data. So on that source data, so this red and blue, you learn a model. Okay, and now you have some unlabeled data, which you can think of the natural questions as the red and blue data, and the gray data is passages from internet about machine learning, and you can use the existing model to generate questions, and you can build a question generation model on the original data as well as maybe this sample data, which is noisy. Okay, so like if you, let's say we are assuming we are building a question generation model. So in order to build a question generation model in self-training, first you would build a source question generation model, which is you take a passage and you try to learn how to generate a question. So that's from the source, and then you sample passages from the target domain, which is machine learning here, and you take a passage and you generate using the source domain model, you generate a question. And now you got passages in target domain paired with the questions in target domain, and you can use this data to train a model. Okay, so this is for question generation. So you have unsupervised data now, and in back training we will do the entirely opposite thing. So in back training, inputs are noisy. We do not know that we have inputs, but what we know is that we can access the a target distribution in some ways. So if you think of a lot of people ask machine learning questions on Reddit. So maybe we already have. So if you're building a question generation model, you're trying to, in fact, have a model that mimics that distribution, right? So we will assume that we have access to that distribution and sample outputs from the distribution, and then we generate noise inputs for the data. So if you think of this, so what we are going to do is first we are going to train both for a given passage we are going to generate questions. For a given question we know how to pick a passage. So this is what we are going on the source domain. So this is natural questions. So once you have both of these models, so you're going to sample a question from machine learning, and that's like a really large Reddit questions or something like that, and that you have access to that. And now for that question you would find a noisy pairing which is on the input side. So you are going to you have a machine learning text, right? And you're going to find, okay, this is probably, this question maybe can be mapped to this one, and now you're going to generate this unsupervised data where you can learn. Okay, all right. And if you go ahead and compare the differences, so the biggest difference is that in self-training, you have noisy outputs, and you're assuming that you're sampling from the source domain, from you're sampling passages from the target domain. Sorry, okay. Whereas your questions are noisy, you are making use of the source model to generate questions. In the back training, you are doing the opposite. We are sampling questions from the target distribution, and we are using the source domain model. We are going to find a noisy input corresponding to this. And you can in the paper we also talk about how to do this for passage retrieval. I'm not going to talk about it here. And for experimental, what we did is, so I'm going to mainly present the results for question generation, also a snippet for passage retrieval. So we have BART encoder decoder to train question generation models, and for passage retrieval we have a dense passage retriever based on BERT. And this is the unsupervised data that we have. We have 50K unsupervised passages and 35K unsupervised questions, and we don't know what their pairings are. These are completely alone, each of them. And if you go and try our models, so what happens is if you take, like, let's focus on question generation here. The metric we care about here is Rouge. And if you don't adapt BART, okay, so get no adaptation on machine learning, you get 31.38. And if you take self-training approach, you do improve, but it's not much. But if you actually apply back training approach, you see huge improvement, even though we never had any access to label data. Okay, so we see that it outperforms by 12 points, and also we saw the same thing with also passage retrieval. We get 9-point improvement. And if you see the training curves, it's very interesting. The training curves, what happens is, so the blue one is actually the back training, and the red one is self training. So what happens is the blue one, as the training progresses, read from right to left, the perplexity on both the training and test decreases. But whereas for the self-training model, the perplexity on the training data decreases a lot as the training progresses, but eventually it starts increasing. The perplexity starts increasing for test data. So it's overfitting the domain. Okay. And if you see qualitative results, so this is if a line is good fit for the data, then the residual plot, so on, so on, so on, right? So if you don't use any adaptation, the question is, what is the meaning of random plot in statistics? And if you use self-training, it's almost the same. It is actually the same in this case. Back training, how do you know if a residual plot is random? And the reference was, how do you know if a residual plot is good? It's a very good output. And we also tested this not just for machine learning domain. We also went ahead and took some existing data sets like PubMed QA and generated questions. So if you see here, this is about the reference question was, are financial incentives cost effective to support smoking and cessation during pregnancy? That's the question. And the question we generate is there a financial incentive for smoking cessation in pregnancy? And the questions for no adaptation and self-training, they're very generic. When do you stop smoking in pregnancy? Okay, so here I showed you that in self-training, inputs are given and outputs are predicted, whereas in back-training, it's the opposite. And I feel like this paradigm is a little explored. So people did explore in back translations in machine translation. It has strong connections to that. But here the tasks are entirely different. It's not a translation task. We have passages, we have natural language analysis. I also encourage you to go check out the GitHub repository if you want to replicate any of these results. Okay, so in summary, I talked about these two models, right? So one, we saw how can we improve the linguistic abilities of language models, and the other one, how can we improve the generalization ability of language models, so that using back training. There are many open problems here. Some open problems are we've been looking at some other phenomena, and language models are terrible at these things like quantification, pragmatics. There's also a lot of recent work by Jonathan recently that came out. And the other thing we are focusing is on how can we have better architectures that incorporate some biases, some human-like biases for systematic generalization. One thing we exploited in back training work is that the problem is dual. Like for a given question, there is a passage, and for a passage, there could be a question. So it kind of worked in dual. That's a dual setting. But what if you don't have dual setting? If you assume that you're trying to build a natural language an NLI classification model, you don't have access to the target distribution that easily, right? And like we are also investigating in our group a lot of cheaper forms of supervision. And so these are very important. Okay, yeah. Before I leave, I want to also advertise a work. This work will be on archive tomorrow. We submitted it on Friday. So this is building on on conversational question answer that we developed earlier with Danchi and Chris Manning. If you see here, the main focus of this is if you are having a conversation, people tend to switch topics meaningfully. They don't switch topics randomly. But can we actually model this behavior and how hard it is? We found out that this is extremely competitive. So here you see from Byzantine Empire after some time we might talk about Mehmed the Conqueror. After some time we might talk about this Turkey and so on. So that we have a lot of this paper we talk about topic transitions. And finally, in AKBC we have a paper on that's on Wednesday. Check that out. It's about how can we detect ambiguity in conversational question answering. Yeah, thank you.
Okay. Thank you, Shiva. Great talk. I can hear Matt. Okay, good.
Yeah, I can hear you. Thank you.
Okay, good. Yeah. So we are a little bit behind. So maybe you have time for like a couple questions.
Okay.
So the first question is about the negative training. So you can also read it from the slide of the interface here. So in the case that iOS was not developed by how do you define a good negative versus a bad one?
Okay, yeah. So in this case, iOS is not developed by and we have a period, right? That's end of sentence marker. We know that we don't want the prediction there definitely, so that it's syntactically not meaningful. So that's definitely a bad. But we are not sampling that as a negative example. That's a bad prediction because we are forcing the model to tell, okay, we don't want Apple there, we want anything other than Apple. The model starts learning that, okay, because you want anything other than Apple, I might start putting a random word there, like a word like the. So that's the scenario here.
Thanks. Okay, so the next question is, can you comment on like whether the unlikelihood training could have other applications to like other semantic phenomena?
Yeah, totally. That's a very good question. Sorry, that's mine. So we are also investigating that. So one is any place where you have language generation. So any task that has some kind of duality nature, you can have the duality nature can be natural language paired with natural language. That's the biggest duality nature that we really care about. But what if you don't have natural language paired with natural language? Can we still apply? And there's a recent work from Google, like Kenton Lee, which showed that you can, if you have access to the target distribution, like on the, if you just have labels, you could still do something meaningful without upsampling just the cases, just the negative examples or positive examples. You can try to follow the target distribution and still do meaningful things. Yeah, so the answer is yes. I think people are exploring this. There still has to be more to be done.
Thanks. Okay, so the next question is negation. Assume that negation doesn't happen very often. Here, if you train and evaluate on negation, because modern negation is the thing that you care about, could you comment on whether training specifically on negation can also improve accuracy or confidence on other like non-negative questions?
Yeah, so if the question is, can we train on, can the performance improve on non-negated things? Yeah, we did see that the performance it does not improve, it is stable, at least. So if you see here on natural language inference, we do see that the performance does not drop on sentences which do not have negation. So it still retains the performance. What it does is it improves on negated sentences. But if the question is, if you train on generic negated data, can the performance improve? That one I'm not so sure. Like if we also tested this. If you train on SNLI negated samples, will it improve factuality? And we found that it does not improve factuality if you just train on SNLI. Like probably that's because the SNLI is small, whereas in this unsupervised way of generating a lot of data, you can generate a lot of data.
Okay, yeah, thanks.
Okay.
Maybe let's just take one final question. Okay. So the next question is, in the negative training, the two objective functions contradict one another. Is that correct, or is this easy to optimize?
Negative tokens, the two objective functions. Yeah, you can say that, yeah, they do contradict each other because we are trying to for the movie is boring, and we are trying to say, okay, the movie is not. Likelihood would say boring is perfectly meaningful, but what we are saying is, given this context, we cannot definitely say that the movie is not boring, right? So because the movie is boring, so if you have a reference, you can create this unlikelihood objective. So they are in fact uh, conflicting, but it does seem to work if you do it in a clever way.
Okay, yeah, let's thank Shiva, and we will have another like 30-minute chat with speaker session very soon. So next we are going to have a
Thank you.
spotlight session coming. Yeah.
All right, yeah, so we'll have a spotlight. I'll play all the videos of the papers. These videos are already on the website, but I think it's good to play. I think I'll be playing 6 videos right now. Then we're going to have chat with the speakers right after that. So for the next talk will be in about 40 minutes or so here. Okay, so I'll just play the...
Knowledge in organizations is stored in different silos, forms, and formats. This makes it difficult to answer basic questions such as, who has worked with this client before? AI can automatically extract business knowledge into a single, consistent, and up-to-date knowledge base, made up of entities that really matter to each organization. We must not forget that this system must operate in an ISO environment, where data sits behind compliant boundaries. To tackle this problem, we developed a generative model for enterprise documents called Enterprise Alexandria. In this model, we assume that entities are stored in a knowledge base with a certain schema that might include a name, a type, and members. A set of templates can be used to convert the entity field into text that might appear in a document. With this process, we can generate multiple sentences mentioning the entities in emails, documents, and meetings. Using Infer.net, a probabilistic framework for running inference in generative models, we can run this process backwards and infer the values of the entities along with the uncertainty in these values. As more documents are observed, we can gradually construct the entire knowledge base for the organization. Our new model, Enterprise Alexandria, is built upon the core probabilistic program of Alexandria, a system designed for web knowledge extraction. Alexandria provides a rich framework for modeling property types such as names, dates, and sets. Some important extensions to Alexandria have been made to allow Enterprise Alexandria to work effectively in enterprise settings. There are 4 key extensions in Enterprise Alexandria. First, structured templates have been added to represent the links between document metadata and entity properties in a latent space. For example, a structured template allows the system to learn that project members often appear as meeting organizers in calendar events. Second, we added the ability to learn the types associated with each entity. For example, we can learn an entity named Firefly is a campaign for a particular organization. Third, Enterprise Alexandria is designed to process documents incrementally with human curators who can edit the knowledge base and add or modify entities at any time. Finally, the entity name model has been extended to recognize separators, case, diacritics, name phrases and acronyms across different mentions of the same entity. Enterprise Alexandria achieves significantly higher precision on 2 real-world datasets. On large-scale runs, it discovers more than 675,000 entities from 1 million documents. It also learns the entity types that are most relevant to the organization. This work is now part of Microsoft Viva Topics, and it is currently servicing thousands of organizations and users in the world. Thank you for your attention, and please come to see our poster.
Is Pierre-Henri Paris. If you come to see me at Gather.town, we will have a nice talk about how to deal with vagueness in knowledge bases. This vision and survey paper is a collaboration with Cyril Elaoud and Fabian Souchanek, all from Télécom Paris, Institut Polytechnique de Paris. So I will start with a small example that is an excerpt from a Wikipedia article. An anti-tobacco sentiment grew in many nations from the middle of the 19th century. This sentence is clearly factual and thus contains information that could be interesting to represent in a knowledge base. However, all non-phrases in the sentence are vague. What constitutes a sentiment? How many nations are many? Does the middle of the 19th century cover the 30s? So the question is, what if we want to extract the information from the sentence and inject it into a knowledge base? How do we do that? To deal with such sentences in knowledge bases, first we had to understand the nature of the phenomenon. Thus, we conducted a manual study on Wikipedia articles where we found that 25% of non-phrases are vague, and we proposed a new categorization of vagueness. The next natural problem is about vagueness detection and categorization. So we conducted a literature review and an experiment on vagueness detection by training a classifier on our Wikipedia dataset. Even a simple classifier already achieves good results. Once detected, the question is now how to represent and reason with vague non-phrases in knowledge bases. Thus, we conducted a literature review about formalisms to represent vagueness. So if you want to know more on the vagueness subject, join us during our talk. You can find more information at this address. Thank you and see you soon.
Multilingual knowledge graph completion with joint relation and entity alignment. Given an incomplete knowledge graph in the form of subject, relation, object triples, AKG completion system fits embeddings for entities and relations, which lets us fill missing subjects or objects in incomplete triples. In the alignment task, some entity and relation equivalences across two or more KGs are revealed, and the system must infer other equivalences. We show that solving these tasks synergistically can improve performance of all tasks. Central to our technique is the subject-object set of a relation. Are capital of and Rajdhani equivalent relations? If Delhi and Dilli, India and Bharat are known to be aligned, and there are many such pairs, that gives us confidence that capital of is the same relation as Rajdhani. But if complex embeddings tell us that Moscow and Moscow are similar, and so are Russian Federation and Rusi Sangh, that also adds evidence. Apart from KGC loss, our system, Align KGC, insists that the similarity between a pair of entities, based on their complex embeddings, tracks the similarity of their BERT embeddings. It also insists that the similarity between a pair of complex relation embeddings tracks a form of soft similarity between their SO sets. Using a unified loss that tracks both completion and alignment, we get large improvements in the performance of all tasks on a recent 5-language KG collection. As larger numbers of gold entity and relation alignments are revealed, our system gracefully improves performance on held-out KGC and entity alignment instances. Details are in our paper. Thank you.
I'm going to tell you about our preliminary results on creating ontology graphs from textbooks. The problem we address is that, given a textbook sentence, we identify the classes appearing in that sentence and the relationships amongst those classes. We solve this problem by adapting pre-trained language model BERT for the tasks of term extraction and relation extraction. The biggest challenge in this process is, where do we get the training data from? For this experiment, for the task of term extraction, we obtained the training data from the glossaries that appear at the end of several open source textbooks published by OpenStax. When we evaluated the BERT model trained in this manner on a textbook that it had not previously seen, we obtained an accuracy of 0.51, which was much better than an accuracy of 0.32, which we could get using a commercial off-the-shelf AWS Comprehend service. For the task of relation extraction, we trained BERT using a weak supervision approach, which also relied on a hand-curated knowledge base. By evaluating this model on relation extraction task, we found that it worked the best on the taxonomy construction and synonym identification task, making it clear that we needed more training data. To gather more training data, we built a crowdsourcing tool using which a person with very little training could identify the correct label between two terms appearing in a sentence. This approach had a very high accuracy in our initial trials. We envision creating these methods into a pipeline, especially by leveraging an active learning approach, so that as we gather more data, the reliance on the human effort goes down and the process becomes increasingly more automatic. Thank you very much.
Hello everyone, today I'm so glad to introduce our paper, Open Temporal Relation Instruction for Question Answering. So what kind of problem we want solved? As we can see in the left side, we want to understand the difference in the questions that indicate the different temporal relations, such as the right after, and before. So our task here is, given a piece of text, our model want to answer the temporal relation questions. And here, there is no explicit time steps in both the context and the questions. In our paper, the contribution here is we reformulated the problem as an open temporal relation instruction task. As we can see in the right side, there are a lot of triplets we extracted from the question answer tasks. And here, why we call the open temporal relation is because the relation in question are so diverse so that we cannot define them in advance. So why we want to use the open temporal relation is because it allows us to model temporal relation in a context agnostic manner, and also it can help us to explicitly model the difference in temporal relations. So here is our models. The model's input is some contrasting questions. And for each questions, we have multiple steps. At the beginning, we have question decomposition to get the open temporal relation and the question event. And after we go to the encoders, we can get the relation embedding and question event embeddings. And finally, we have answer event selection to get the final answers. So this is basic architecture of our model. And also, we like to show our results. So our model have great performance compared to our other baselines. And in addition, you can see our model is much more data efficiency. So for more details, please check our paper. Thanks.
Temporal knowledge graphs contain information indicating relations among entities at different times. For example, geopolitical knowledge graphs include coded interactions between socio-political actors. Left figure is an example of a geopolitical knowledge graph. Most of the real-world knowledge graphs suffer from incompleteness, and most existing KG completion methods rely on a sufficiently large number of training examples per relation. However, most real-world knowledge graphs have a long-term structure, meaning that many relations occur only a handful of times. The data scarcity issue is exacerbated for temporal graphs, since the dynamics governing the evolution of those graphs might be highly non-stationary. First, new types of relations or events might emerge that have not been observed before, and furthermore, even if a given relation has been observed frequently over some time interval, the distribution of occurrences over that interval might be highly inhomogeneous and bursty, as you can see in the right figure. To alleviate this issue for a static knowledge graph, several recent studies have focused on adopting few-shot learning methods for KG reasoning under the condition that only a few triples are available for each relation. But those methods are not able to incorporate the temporal dependencies that often exist in temporal knowledge graphs and may contain crucial information and insights about the data. In this work, we propose a method for predicting new events for unseen relations and unseen timestamps in temporal knowledge graphs when there is only one training example for each relation. Our model can effectively encode an entity's interactions with others from L previous times by leveraging a self-attention mechanism that sequentially aggregates an entity's neighborhood over time and extracts a time-aware representation for each entity. Furthermore, our model employs few-shot episodic training to learn a similarity metric between a training entity pair and a given query entity pair, which indicates the likelihood of a given relation between the query entity pair.
Sorry, yeah, that was the last spotlight. So I encourage everyone to go to the chats and posters room. The poster authors probably won't be there, but there will be other attendees and definitely the invited speakers. So you can chat with them, ask them questions that we didn't get to or other questions that you have. Thank you, and see you everyone in about 25-30 minutes.
Hello?
Okay, we're live, I think.
Oh.
Okay, hopefully everyone is back from the chats and posters. Maybe we'll wait like 20 seconds to let people move from one virtual spot to the other.
Let me see if screen sharing is working.
Yeah, you should share.
Is it good?
Yeah, I see it. I see the bar at the top. Yeah, now it's full screen. Okay, so I think we can start. Hopefully everyone found their way through the huge space. So it's my pleasure to introduce our next speaker in the second session, Percy Liang, Associate Professor of Computer Science at Stanford, did his PhD at Berkeley with Dan Klein and Michael Jordan. And Percy is really exceptional in the breadth of his interests. He has managed to make foundational contributions in fields like natural language processing, machine learning on the theory side, on the applied side, structured prediction, and even programming languages. He's been done a lot of work on semantics, including semantic parsing around 2010. We're in the second revival. And now he's been working a lot on interactive learning, robustness, interpretability, and reproducibility. He recently became the director of the Center for Research of Foundation Models. That attracted a lot of attention. I'm sure many of you have heard of it, where multiple scholars work on what we typically call large pre-trained models or language models. His work has been recognized by many awards, including the Presidential Early Career Award for Scientists and Engineers, the HKI Computers and Thought Award, and the NSF Career Award, and many more best papers in ACL, EMNLP, ICML, and COLT. On a personal note, he was my postdoc advisor, so you can trust me when I tell you that he always has something interesting to say, so I'm really looking forward to this talk. So you can take it away.
All right, thank you, Jonathan, for that wonderful and very thorough introduction. So thanks everyone for being here. This is my first time using StreamYard, so I hope it will be okay. So the title of my talk is Knowledge, Language Models, and Adaptation. This is joint work with my students, Lisa, Lee, and Michael, and Tenry, who's not my student, colleague. I want to start by taking us back to 5 years ago. So this is when I gave my first and only talk at AKBC. And it was a very different time. So the talk was called Querying Unnormalized and Incomplete Knowledge Bases. And at that time, I was really interested in semantic parsing. So the goal of semantic parsing is take sentences such as what is the second most populous city in California, convert it into some sort of program or a logical form that can be executed on a knowledge base or a database to get out an answer. And because you're able to capture the full semantics of the actual question, you can do really fancy things like ask the question which state's capitals are also their largest city by area. And this works, pretty well. We were looking at Freebase at the time, which was a big knowledge base created by Google. Unfortunately, died. But on the other hand, there was also this thing that kept on driving me crazy, which is that there were a lot of questions and queries which were not in Freebase. And in fact, we had this data set with Jonathan where fewer than 10% of the questions were actually answerable by Freebase. So we could go down this route of collecting better knowledge bases, doing knowledge-based construction. That's a lot of the kind of this AKBC is concerned with. And but that takes a lot of energy and time, and I was wanted to see if I could really circumvent that. So we embarked on a line of work that was trying to do more end-to-end question answering, where the end goal was driving the construction of intermediate knowledge representations. We did a lot of work on expanding to beyond Freebase to tables on the web. So leaving the knowledge and its kind of basic raw format, which is semi-structured, and querying it, and also looking at even semi-structured web pages such as lists and things like that. What we upon reflection, I think that we were a little bit too aggressive with the end-to-end. Right, we were looking at a question, and there's all this stuff that's out there, and we were trying to learn a mapping to how to answer that question. And I think there was a lack of shared components, which is a point I want to get back to later in the talk. So at the very same AKBC, Chris Manning gave a very different talk, which was titled Text as Knowledge Bases. He had been going around proclaiming like, we don't need knowledge bases, we just have text, and text is, all that we care about. So there was this kind of revival around the time around kind of machine reading or machine comprehension. And the idea is that, well, the text is there, so all you really need to do is a machine that can use this augmented quote unquote knowledge base, which is the text, to answer any sort of questions. And if you could do that, you'd be good. And that same year, we created the squad question answering data set, which had got a lot of people working on it. And at this point, reflecting back over the last 5 years, it's just been a lot of work on question answering, both kind of open domain especially, and also more kind of spam based. And now it's just kind of actually very successful as a service that you can use. You can ask Google a question and it kind of works most of the time. And this is, I think, by far the most, I would say, successful. Chris was right in a sense that it was a kind of a most successful way of harnessing the kind of quote unquote knowledge that was out there. But times change, and 2018, 2019, we saw a kind of revival of interest in large language models with Elmo and BERT. And there was this kind of interesting, thought-provoking paper called Language Models as Knowledge Bases in 2019. And the idea is, well, do you really need a knowledge graph? Maybe we can just probe language models. Language models are trained on all this text that has the knowledge in them. Maybe we could just ask a language model to just fill in the blanks. Dante was born in Mask, and then would magically predict the right answer. And this kind of works to some extent. So this has also been extended on in various ways. But I want to point out that in some sense, the knowledge that we're probing out of these language models is, these facts are actually not really the most interesting things. The most interesting things is, taking a kind of I guess a leaf from Jeff Hinton's book. It's dark knowledge, right? Basically, if you have, let's say, a book is a collection of written words, and you prompt what other words can complete this, you say printed, paper, sheets, writing, information, and all with a kind of the rich and nuanced set of conditional probabilities. And I would say that it's really the kind of this rich abstract knowledge that's inherent in these conditional probabilities, which makes the language models helpful, not really the kind of the individual facts, although that's there as well to some extent. So to summarize a little bit, we've seen kind of three types of knowledge, and I'm going to judge them on three axes: how transparent they are, how much they do as synthesizing disparate facts, and how open-ended they are. And it's one of these situations which is you can pick any two, but you can't have all three. So databases or traditional knowledge graphs are transparent. They have very clear semantics, which allows you to be able to answer compositional questions and synthesize information across a wide set of individual facts. But the main problem with this, which has been kind of a problem that was hitting my head for a very long time, was that they're not open-ended, right? They have a fixed schema. They often have missing facts. And so you can only, or you're kind of upper bounded by how good the database is. The second form of knowledge is you can leave it in text, right? This is open-ended because text is in some ways kind of universal. They're also transparent because when you ask a question, you could just point to the piece of text. And this is the only way that question answering on Google actually is somewhat trustworthy. You can validate if you believe the answer or not. The main limitation is that they're not synthesizing. You can't ask super complicated questions that need to pull information from different pieces. And so you're basically bound to kind of this more strict retrieval. If basically the answer that was written somewhere on the web, then you can get it. If it was not, you can't do much. Of course, you can extend this with multi-hop question answering, but fundamentally that's kind of just a small step compared to the space of all questions that would be possible. And now the new kid on the block is language models. And they're open-ended because they're trained on a lot of text. They can synthesize information through the parameters of a neural net, but they're really not transparent, right? So they can they have a lot of capabilities, but who knows what's going on inside them? Sometimes they lie, sometimes they surprise you with actually the right answer, and this is a big problem. So you can kind of pick the two criteria that you want, but at least right now, we don't have a way of realizing all three. So I'm going to spend a bit more time talking about language models, or what we've been calling foundation models, which is supposed to be a kind of a generalization of language models that captures vision. So foundation models aren't just language models, and also accentuates a kind of important property. The idea is that if you look back before 2019, or even longer, right? It used to be that every area in NLP was kind of its own area. You have people creating a set of data sets, evaluation metrics, methods, which were all kind of different in some way. And over the years, things have been kind of homogenizing, and to the point where after BERT came along, you suddenly kind of enter this paradigm where you have a single foundation model, in this case, a large language model, or mass language model, such as BERT, kind of powering all of these different applications. And this has been the kind of prevailing paradigm. So if we think about the foundation model as the kind of the knowledge base somehow, then the question becomes, how do you extract or harness the information that's in this foundation model for a given downstream task? So I want to spend the next maybe bulk of the talk talking about two projects where we've explored this question of adaptation. How do you adapt the foundation model to a downstream task? And we'll show how this idea of preserving the information in the language models turns out to be a useful idea. Okay, so the first project is called prefix tuning. This appeared at ACL this year, my student Lisa. And the task setting is you're given a structured table of information. You want to generate a text that realizes the information. So nowadays, the thing to do is you go download the largest model you can online and fine tune it. The problem with that standard fine tuning is that GPT-2 XL has 1.5 billion parameters. And if you were doing this for a number of different tasks, you would have to mutate all 1.5 billion parameters and store different copies, which was very inefficient. And from the point of view of if you just as a tangent, if you think about OpenAI or other people exposing APIs, you really want APIs that allow customers to be able to fine tune, and they're not going to store a huge GPT-3 for every customer. So then there's the idea of light fine tuning. You can tune only the top two layers, but this loses accuracy. There's been a line of work starting in 2017 on adapter tuning, where you can actually get comparable performance by tuning only 3% of the parameters. Now the question, can you go even farther by reducing the number of tunable parameters? So here's an extreme case. So GPT-3 can do in-context learning. So here, you just have a language model. You don't do any backprop, but you concatenate some instruction with a set of examples in the input, and you just ask the language model to spit out an output. And this actually, works to some extent, surprisingly. But the main con is that you can only train on a few examples. So good luck trying to fit 10,000 examples. And you need these large models. So GPT-2 can't really do in-context learning reliably. But we can take inspiration from in-context learning and this idea of prompting and see if we can get kind of marry the idea of prompting, which is about conditioning, and fine-tuning, which is about kind of gradients. So suppose you wanted to have a system that can map countries to their capitals. So the name of the game is to construct a prefix. So you try to prepend some words such that if you feed this into a language model and ask for its most likely output, you have a chance of getting the right answer. And you could, if you want to do the table to text generation problem, Well, you could try to serialize the table in a string, and the prefix becomes maybe a little bit harder to think about, maybe describe a table or something, and you could try to ask the language model to produce an output. And this might be a little bit wishful thinking. So the question is a prefix even powerful enough to specify the task, especially if you have 10,000 examples? And even if it were powerful enough, how do you find one? So this is kind of like, I think about a language model as a kind of a wild, animal, which has a lot of potential, but really needs to be the potential needs to be harnessed somehow. So this kind of idea of prompting is like you're sticking these little treats in front of the language model and seeing if it can get it to do the right thing. So you could try to do a discrete search in this space for the right prefix, but discrete search is always kind of annoying. So what we're going to do instead is to do something more continuous. And I'm going to set up a little bit of notation so I can introduce the idea. So here's input X, sequence of tokens, output Y, sequence of tokens. Z is going to be the concatenation. And for each token, input and output, I'm going to have a hidden or a latent vector, HI. And AI is just going to be computed autoregressively based on the previous hidden latent states and the given token at that point in time. So given this, so this is a kind of black boxing the fact that it's potentially a transformer architecture. So now you can go and you fine tune all the parameters, but this is expensive, as we've said before. So the idea with prefix tuning is to pretend that there was these virtual tokens at the beginning, so which we call the prefix. They're not going to be tokens for reasons I'll explain later, but just it's maybe helpful intuition to think about them as virtual tokens. So now we define the hidden state as theta i's if we're in the prefix. So each prefix hidden state is a free parameter that we can tune however we want. And then the rest is the same. So we're using the language model, and we're not touching the language model parameters here. We're just only touching the prefix. So pictorially, what it looks like is that we're only tuning the prefix parameters, which is the number of parameters, the number of layers times the dimension of each layer times the prefix length. In this case, it's 2, but we can make it a lot longer as well. So how does this work? How well does this work? So here is an example data set called E2E, which is restaurant reviews. So here we have the input, which is the structured information about the restaurant, and output is natural language description. So here I'm plotting how well we do based on blue versus the number of the percentage of tunable parameters that we're allowing to change. And full fine tuning is here. We're tuning all the parameters. We get some blue score of like 68 point something. If we fine tune the only top 2 layers, the accuracy goes down a little bit. If you do adaptive tuning, interestingly, the accuracy is even better than if you did full fine tuning at 3% of the parameters. But if you really are parsimonious and say adaptive tune with 0.1% of the parameters, it's actually a lot worse. Prefix tuning at 0.1% of the parameters actually does remarkably well, better than any of the other methods. So this was actually kind of surprising in a good way to us, where we initially set out to reduce the number of parameters, but we actually showed that we can, in some cases, do better than if we had the full set of parameters to work with. Here's another data set, WebNLG, which is describing entities. The same trends hold. It's a harder data set, so we end up not doing as well as full fine tuning, but we're comparable. And Dart, we're doing at the end at 0.1% of the parameters, comparable, or even maybe a little bit better than full fine tuning. Whereas adaptive tuning doesn't work nearly as well there. Summarization. It's harder. Summarization data sets are much longer, more examples. So prefix tuning, even at 2% of the parameters, wasn't able to exactly keep up there. So, but one thing that I think is really interesting besides just the kind of the raw reduction number of parameters, is extrapolation. So we did this study where we trained on, this is WebNLG, so we trained on text which involved a set of categories, and we tested on unseen categories. So some of the relations, such as birthplace, were shared, but some of them were unique. Like we never saw genre at training time. And on this split, we saw that fine-tuning methods don't work very well at all, presumably because they overfit. But the methods that actually work well are adapter tuning and prefix tuning, which preserves the pre-trained LM. So we have this hypothesis, intuition, that preserving the language model is important for extrapolation. So to wrap up this section, we talked about prefix tuning, and the key idea is lightweight fine-tuning via standard backpropagation, plus this idea of conditioning, which is gotten from the in-context learning or GPT-3 style, or prompting, I guess. And we saw this is really effective at 1.1 per 7 of parameters on these 3 natural generation tasks. We actually do comparable, if not even better, than standard fine-tuning. And also this has a unique probability of being able to extrapolate better out of domain. I think there's a bunch of open questions here. So on summarization, we weren't able to do as well. And then why does prefix tuning work? Is it because it's preserving the LM or because of something else? So the second project I want to talk about is maybe gives another data point to that last question. It's called composed fine-tuning. This is a work that appeared at ICML this year with Michael Xie and Tony Ma. So the starting point here is instead of using a standard autoregressive model, let's take BART. So BART is a disjointing autoencoder for sequences, and it's trained to reconstruct an output from a noisy input, which might be filling in the blanks or some sort of other perturbation of the output. So given a BART model, the standard practice is just to fine-tune on some label data. But is that really the best way to adapt these models? So we took an example synthetic data set for pseudocode to code translation, which we call sense type. So here is the input. It's pseudocode. And what we're trying to do is produce the output, which is the C++ program. And the data set is set up so it's a kind of a line-by-line translation. It involves a little bit of syntactic rewrite, but nothing too fancy. The interesting thing is that the input does not have any types in it. But the output, you need types in C++. So the prediction has to do some sort of type inference and impute the types. So we did this experiment where we took a pre-trained denoiser, which was pre-trained on a bunch of source code, and we can use this in 2 ways. So we can initialize it and fine-tune. So this is like standard practice, and we get the base predictor, which we call the base predictor, and then we also use this denoiser unmodified, and we just compose these two. That's why this idea is called composed fine-tuning, which we'll see later. So the intuition is that the base predictor is just going to predict and hopefully capture the local structure, because that's kind of the easy part. And then the denoiser is going to, because it's trained on more data, because it doesn't need supervision, it can fix up the global structure by doing kind of global type inference. So if we do this strategy, basically initialize, fine-tune, and then just apply the same denoiser, what we see is that the accuracy goes up after applying the denoiser. So this is interesting because in some sense, this is kind of a very baseline idea. So you're just doing what you did before, and then you say, here's the denoiser, and just apply it again to basically smooth out the output and make it more look like code. And this bump in accuracy suggests that there seems to be value preserving the original language model. But we can go one step further than that. So remember, before we were just initializing the base predictor and fine-tuning it in a supervised way based on the label data, we can actually train the base predictor with knowledge that we're going to do this denoising step in the end. So the objective function is that we're going to think about the base predictor as a policy, kind of in reinforcement learning. So the policy is going to generate a particular prediction, and the reward is going to be the log of probability of the correct answer given that prediction. So the pre-trained denoiser is going to act as kind of a reward function here. And then to kind of regularize it, because RL is kind of annoying and hard and potentially unstable, we're going to add this term, which is the original kind of fine-tuning objective as well. So the results here are interesting. So we looked at two data sets, the sans type data set, which is synthetic, and Spock, which is this pseudocode to code generation data set, which we put out 2 years ago, which was crowdsourced. And we're going to also pay attention to out-of-domain accuracy. So we see that if you look at standard fine-tuning compared to composed fine-tuning in green, we see that there's a consistent improvement in the accuracy, especially on out-of-domain accuracy. So it shows that composed fine-tuning is effective at producing a better fine-tuning strategy. So I want to summarize so far. We looked at prefix tuning and composed fine-tuning. Both have the shared intuition that we want to preserve the language model as much as possible. And this is really highlighted nicely in experiments on assessing out-of-domain robustness. And if you think of intuitively, this kind of is reasonable, right? Because you have a huge language model, you have limited label examples, and if you just go in there and you start doing gradient updates, you're kind of messing up the language model, which has been kind of carefully tuned on lots more data. We're actually working out some theoretical analysis showing how doing this fine tuning on a subset of label data that's not representative of the entire space can kind of render some of the representations a little bit more inconsistent. So I think this is an important intuition to keep in mind. But more broadly, I think these two are just examples of a much larger space of fine-tuning adaptation strategies, which we can use to harness these large language models. So this is something that we should be kind of exploring, I think, a lot more. So I want to just conclude with a few remarks. So here is a quote, which I'll read for you. The point is that computer programs are being given ever more responsibility, ever more complex tasks, and ever more sophistication. But their inherent intelligence and sophistication still vastly exceeds the true depth of their understanding and breadth of their capabilities. They are especially susceptible to failure when confronted with novel or unexpected situations. They are, if not complete idiot savants, at least extremely brittle. So now, unfortunately, if this were a kind of a live, well, it is a live talk, but if I could see the audience, I would love to see a show of hands to get people's guess on where this quote comes from. So you think about where does this come from? What era does this come from? It turns out that this is actually taken from the intro chapter of the book called Building Large Knowledge-Based Systems, which is the Psych book. So Psych, for those of you who don't know, there's this project in the 80s who tried to write down in a structured knowledge-based format all the kind of common sense knowledge in the world. And this is kind of interesting because what was the contrast back then? Expert systems were these computer programs that is being described here, which were very narrow, built to kind of very specific use cases. And in the narrow use case, they worked, but they often had these brittle failure points. And Psych was a project that was meant to develop general purpose knowledge that would be shared across multiple different applications. So this book was written in 1990, and sadly, this Psych program maybe did not lead to the kind of the general all singing, all dancing knowledge representation that would power our AI systems. But kind of this contrast is, this quote could have been taken from, today, which is interesting. But this general idea of knowledge is, I think, an important one that I think we should be paying more attention to, especially in recent years. So the model here is that build once, used for multiple applications. So traditionally, through the history of kind of machine learning as applied to NLP and other domains, we've been very good at building kind of one-off, systems that you gather a label data set in a given domain, you train on it, and it works well in that limited domain. But what we're seeing with these, but the general idea of having knowledge is that knowledge is something that's general purpose, that you can share and you can use to kind of, you gather knowledge and you can apply it to many different settings. And so today, the closest thing we have to this kind of general knowledge are these what we call foundation models, which include large language models, but also vision models like CLIP. And these language models, as I mentioned on a previous slide, are very open-ended. They capture a lot of information. They're abstractive, so they can really kind of get at these general patterns, but they're also not very transparent. And so I think it's helpful to kind of embrace this vision of having general knowledge that powers a lot of applications, but then really work on figuring out what this foundation or general knowledge should look like. Can we evolve language models to make them more robust or transparent, or should we be kind of having some sort of more hybrid approach or so on? So this is a open question that maybe in 5 years we can reflect on. Okay, so that's it, and thanks for your attention.
Okay, so thank you, Percy, for the inspiring talk, and we have a few minutes for questions, so I'll jump right in. First question, most upvoted. Do you think prompt engineering will disappear in a couple of years or not?
That's a good question. So I think that prompt engineering I think that let's say that if you care about the application, I think you should not be using prompt engineering, because you should gather a bunch of examples and fine-tune and not pray that things will work. Prompt engineering, I think, is, from a research perspective, interesting. It can allow you to maybe probe into this language model, and it can be kind of fun. But I would definitely think that if you're serious about your application, I don't think I would recommend it.
Cool, thank you. A question from Ronin Wu. Thank you for a nice talk. Apology for the maybe naive question. Can you elaborate a bit more on how prefixes in the model are generated? Can I understand it as an additional layer of classifier applied on the text entities before feeding them into the language model?
Yeah, so the prefix is just a set of 3 parameters. They're vectors, which are learned through backpropagation on your labeled training set. And they're, in some ways, just to address the kind of additional layer, they're kind of at the very bottom, because they're the prefix tokens show up at the very beginning, which means that everything else, the input and output, kind of depend on them. So as opposed to being at the kind of very top, which would be what kind of you would expect from kind of programming.
Yeah. Thank you. Let's take maybe a couple more. Can you elaborate why you think you cannot synthesize information when using text? Can't you retrieve the relevant text and reason over it?
Yeah, so what I mean by synthesizing information is taking a lot of text. Maybe you get, you're doing research on, what is the best place to live in 2021 or something. So yes, you can find a page that talks about it, but presumably there's going to be a lot of pages about this information, and you want to synthesize together. You could do, I guess, a little bit of that. I guess if you think about multi-document summarization and things like that, can get you a little bit farther along that route. But when I talk about kind of the very abstractive information that involves reasoning over an entire corpus of text, I think we need a qualitatively different mechanism rather than just retrieval.
Thank you. I think we will stop here. There are many questions. I really encourage everyone to come and chat with Percy. He will be a little bit late, possibly, to his Gather.town chat, but be patient. So thank you very much. I also wanted to ask everyone, in general, if you can, this is a virtual conference and we're on Gather.town, and the more people turn on their videos, video cameras during the streaming sessions, during the poster session, during the chats with the invited speakers, I think the nicer it will be for everyone. So I really encourage you to do that. So I think we can move on to the next talk. Okay, great. So it's my pleasure now to introduce our next speaker in this session, Peter Clark. And Peter is a senior research manager at the Allen Institute for AI, where he leads the Aristo team. And he has been heavily involved in research at the intersection of natural language processing and machine reasoning and common sense reasoning and world knowledge for nearly 30 years, with many contributions in knowledge acquisition, knowledge engineering, knowledge representation, and many, many more. He was a leading figure in Project Halo 15 years ago that already then proposed to develop a model that encompasses all scientific knowledge for question answering. And this has led to many interesting contributions in question answering and textual entailment. And at AI2, his team, Aristo, worked for a long time on building models that pass science exams. And in 2019, they actually had a model that got more than 90% score on the grade 8 science exam. Peter received many awards, including Best Paper Awards in AAAI, EMNLP. He's a AAAI senior member. And in recent years, he's been working a lot on models that perform reasoning and combining pre-trained language models with the ability to reason explicitly with explanations. So I'm really curious to hear what he has to tell us. So you can go ahead.
Great. Thanks a lot, Jonathan. So thanks again for putting on this super interesting conference. I attended some of the early ones years ago, and it's great to see how much it's grown. So I'm Peter Clark. I'm at the Allen Institute of AI. I'm going to talk about some of the exciting work we've been doing the last couple of years on teaching models to reason systematically. Before I do that, I'll just give you a quick picture of here's Seattle. This building down here is AI2, so you can get a visual picture of where we are. Unfortunately, with the pandemic, I've spent most of my time more in this environment. This is my basement where I kind of hang out and have been working remotely. So let me first talk about knowledge-based construction, the title of this conference. And our conception of what a knowledge base is has changed radically over the last 10 years. So in the old days, going right back to John McCarthy in the 60s, a knowledge base was thought of as a formal encoding of the knowledge we were interested in. And Percy alluded to this in his talk just now. And why did we do this? Well, this allowed our systems to draw valid conclusions using well-defined inference procedures. And I myself have spent a couple of decades working on this kind of model of a knowledge base. But this picture has changed pretty radically in the last 10 years. And we now know we can cram a vast amount of knowledge directly into a language model. But the question that then arises is, well, how do we then get language models to use that knowledge appropriately? And by that, I mean, have it draw valid conclusions given what it knows, hopefully with an explanation for its reasoning. So you might ask, well, why do we even care? Language models already pretty good at question answering. So let me just give you 4 reasons why we should care. First of all, and several speakers have alluded to this, despite language model successes, they're known to be very brittle and they can make catastrophic mistakes, providing answers which simply aren't justified by all the things that they know. And Siva this morning gave some great examples of that. And then second, even worse, language models can't explain how they come up with their answers. And even worse than that, if we can't understand what they're doing, it's very hard to correct them besides simply throwing more data at them and hoping. And in contrast, people can explain their reasoning. We can have arguments. We can correct a reasoning if there's some errors or misconceptions in it. And finally, just stepping back and thinking about the bigger goals of AI, coherent reasoning and explanation are pretty fundamental concepts. And if we want the field to make progress, we need to go beyond black box QA systems to something that's a bit richer in terms of the information they can absorb and how they process it. So as a quick outline, I'm going to present work we've been doing in this area for the last couple of years, trying to get modern systems to reason systematically. First, in synthetic environments where users provide all the knowledge, and then secondly, in real environments where reasoning is over the knowledge pulled out of the pre-trained models themselves. And I'll spend most of my time talking about this. And then finally, if a model can articulate the latent knowledge it used in coming up with an answer, this offers some new opportunities for teaching our systems. So rather than just kind of throwing a lot of examples at the system and hoping, we could potentially have a dialogue with it and correct its bad beliefs directly. And so this is a speculative part that I'll touch on at the end. So first on reasoning in synthetic environments. So at last year's AKBC, Ornette Sioni is AI2. He presented some of this work. So I'm just going to spend 3 minutes recapping this. And so the question we were asking was, can we retrain transformers to reason systematically over the facts and rules that we give it? And surprisingly, the answer is yes. And we built a system rule taker that does exactly this. For example, if I give it some facts and rules like these ones, nails are made of iron. If something is iron, then it's a metal. If something's made of metal, then it can conduct electricity. And now if we ask a question, do nails conduct electricity? Rule taker will come up with the correct answer, true, that's entailed by these facts and rules that I've given it. And we showed that a neural system could do this reliably over significantly larger rule bases and with more varied natural language descriptions of the rules and facts, and requiring longer reasoning chains than seen in training. And more recently, we extended this to also generate the proofs for its answers. And I'll just play a quick demo here of that system in operation. So here again, I'm entering some facts and rules. If something is a metal, then it's a conductor. If something's not a metal, then it's not a conductor. Iron is a metal, nails are made of iron. And then is it true that nails are conductors? So the system chugs away and comes up with the correct answer, true, but also generates a proof of the answer. Nails are made of iron. Iron is a metal, therefore nails are metal, therefore nails are conductors. If I change this to a counterfactual situation, I say iron is not a metal, and now re-ask the question, again, it comes up with the correct answer, now false, and again generates the derivation of that conclusion using the facts and rules that were given at the beginning. And just to show some robustness to the language, I can rephrase that first sentence as something like, metal things happen to be conductors, and then re-ask the question, and again, see what it does. And again, it comes up with the correct answer, true. And again, it's providing the explanation. So again, this is generated with a trained T5 model. So the trick to building these systems is to train them on large numbers of synthetic reasoning problems. So we generated those using a formal reasoning engine and then converted them into pseudo natural language. And it's quite remarkable that transformers can be repurposed like this. But of course, in these examples here, I'm providing all the required knowledge explicitly, which is clearly not scalable. So how might we extend this to use knowledge that's locked up in the transformer itself? And this brings me to the second part of the talk, where I'm going to spend most of my time. So to move into the real world, the biggest change that we've made is to replace logical deduction as the key reasoning operation with textual entailments. That is the kind of inference step that you or I would naturally make. I kind of like to think of textual entailment as deduction with some of the obvious steps skipped over. Unlike with rule taker, if we want to teach a model to generate valid reasoning chains constructed out of textual entailment steps, we need a lot of examples. But it's not so easy to synthesize entailment examples automatically. Although, let me just mention that Greg Durrett and his team at UT Austin have had some impressive success at this. So what we did instead was to spend a considerable amount of time and effort earlier this year building a new resource called Entailment Bank, which is a large data set of about 2,000 entailment trees with about 5,000 entailment steps. So just to describe that resource, Entailment Bank consists of, each example consists of a hypothesis, like this one, eruptions can cause plants to die, and a set of sentences that are pulled from textbooks that are relevant to the hypothesis. And then we had a bunch of annotators then build these entailment trees, showing the chain of reasoning from the facts that were given at the beginning to the hypothesis that we're interested in. So in this case, eruptions can cause plants to die, is entailed by eruptions block sunlight, and plants will die without sunlight. And similarly, eruptions block sunlight is entailed by eruptions produce ash, and ash blocks sunlight. And the annotators as well could modify the text sentences that were included at the beginning if not all the information that was needed for their trees was included. So now what we want to do is train a system to see if it can generate a valid chain of reasoning given a new hypothesis. And we went through a number of iterations to try and do this. And after a lot of experimentation to find out what worked best, we ended up doing 3 things to leverage this resource. So the first thing we did was we ended up training the system to just generate 1 deep trees. In other words, just the top level of these entailment trees. This turns out to be easier to learn for a generative model. And of course, as you can probably see, we can reuse the subtrees from the original data set as additional examples. Second, for some examples, we mask out some of the required knowledge in the inputs. And this encourages the model to fall back on its latent pre-trained knowledge to kind of fill in the gaps. And then thirdly, for a large number of examples in the training, we don't provide any of the facts. And this forces the model to completely use its latent knowledge when generating trees. So we trained a generative model, which is able to produce valid chains of reasoning about half the time, depending on the data set. And let me just give a couple of examples of some of the outputs. So in this example, if I give the trained model the hypothesis, plants require CO2 to make their own food, the system generates the following chain of reasoning to support that. A plant requires CO2 for photosynthesis, and photosynthesis makes food for the plants. And another good example is if I ask it to explain why blacktop is a good surface for roller skating, it generates the explanation. Roller skating requires a smooth surface, and blacktop has a smooth surface. So the model here has picked up the style of textual entailment reasoning chains from the training data, and it's also here leveraging its pre-trained knowledge in order to generate these statements. But as it's been trained only on positive examples, if I give it a false hypothesis, it will still try and generate chains for these. So for example, if I tell it that rabbits have 6 legs and ask it to generate a chain to explain this, it will generate the following chain. A rabbit is a kind of animals, and animals usually have 6 legs, something which is clearly false. And in fact, something which the model itself doesn't believe. That is, if I ask the model, do rabbits have 6 legs? It'll tell me the answer is no. So clearly, to get faithful chains of reasoning supporting hypotheses, we need more than just naive generation. So what we've done is we've moved to a system that instead of just generating strings and symbols, does more of a kind of thoughtful construction of reasoning chains. And the system is called Entailment Writer. And the I/O behavior is as follows. The input is a question. do plants require CO2 to make their own food, for example? And then the output is the answer. So here it thinks the answer is yes, and the chain of reasoning that supports that. A plant requires CO2 for photosynthesis, and photosynthesis makes food. Now, inside Entailment Writer, there's actually a collection of 4 separately trained neural models, one which answers the question, one which generates a chain of reasoning, and then 2 others which attempt to verify that chain of reasoning. This is essentially to check that the model believes what it's telling you. Engineering-wise, we could have implemented this as a single model with multiple facets. In fact, in the early versions of this, we ended up with 4 separate models, but that's an engineering detail. And what I want to do now is just illustrate how these different modules interact. So what I'm going to do is just talk through this example. So first of all, I asked, do plants require CO2 to make their own food? The controller sends the question to the answer generator, and the answer generator gives its kind of reflex answer of it thinks the answer is yes. Then the proof generator tries to generate a chain of reasoning to support this. It generates plants require CO2 for photosynthesis. Photosynthesis makes food. And then the verification module kicks in to check whether the model actually believes what it's saying. So first of all, it asks, is it true that a plant requires CO2 for photosynthesis, and sends that to the answer module? And if the answer module says yes, that's good. And similarly, does photosynthesis make food for the plant? Again, if that verification test is passed, that's good. And then finally, another verification step checks the entailment itself, namely, do the 2 premises that were synthesized really entail the hypothesis here? And again, this is trained on the entailment-backed data. And if that entailment step is passed, we end up with our desired output. We end up with an answer that is supported by a chain of reasoning. This whole system has 4 very nice properties. First of all, it's producing answers supported by a reasoning chain that's faithful to the model's own beliefs. We validated that these statements that have been generated here are actually consistent with the model's latent knowledge. And in other words, we can view what we're seeing here as a kind of articulation of some of the latent knowledge in the system that justifies a hypothesis. The second nice feature is we can do interactive drill down explanations. So for instance, I could ask, well, why is it that a plant requires CO2 for photosynthesis? And we can call the whole machinery recursively to have it now go 1 step deeper in terms of explaining the answer. So it might generate a photosynthesis converts carbon dioxide and water into carbohydrates and food. And if a plant converts something, then that plant will require that something. And then thirdly, and I think this is the most exciting aspect, if verification fails, we can back up and search for an alternative proof. And if we can't find any alternative proofs, we can back up further and have the answer generator change its answer. So for example, suppose the proof generator had generated a chain of reasoning like this one. Plants require CO2 to make food because plants require sunlight, and sunlight is a kind of carbon dioxide, something that's clearly false. Now, when the verification step kicks in, it will try and verify whether the model believes sunlight is a kind of carbon dioxide. It'll fail this test. And so now the system can back up and we can generate an alternative chain of reasoning, perhaps the one that's shown here. And we can do that by using techniques such as nuclear sampling in the generation procedure. And if after several attempts we're unable to generate any chain of reasoning that justifies the conclusion, we could even back up further and have the answer generator select an alternative answer. And so this whole system is a bit like a person who gives an instinctive answer to a question and then kind of thinks about it and then says, that doesn't kind of make sense. I think I'm going to change my mind. And so there's kind of an important interplay going on here. The answer module is conjecturing answers for the proof generator to explain. And then the proof generator determines which of those conjectured answers to trust. So you could think of this a bit like the kind of fast thinking, slow thinking style of reasoning. And it's also important to note here, the proof generator is thus not just doing post hoc explanation, but it's playing a role in the answering procedure itself. So let me just illustrate this again in a bit more detail with an example. So here I'm asking the question, can a plant photosynthesize if it has no leaves? The system comes back and says, I don't think it can. A plant cannot photosynthesize if it has no leaves, because the leaf performs photosynthesis, and photosynthesis won't work without leaves. Now, if we look at the trace of what's going on inside, and I'm just going to reveal some of the system's reasoning here. When the system starts, it initially conjectures the wrong answer to this question. So it thinks that a plant can photosynthesize if it has no leaves. And now it tries to generate a chain of reasoning to support that. And it generates a leaf performs photosynthesizing, therefore plants cannot photosynthesize without leaves. And then the entailment checker says, does that entail that plants can photosynthesize with leaves? That's not a valid entailment, and so it gets rejected. And so the system tries again to generate a chain of reasoning, and again, and again. And eventually, after enough tries, it gives up and says, hey, I can't prove that a plant can photosynthesize if it has no leaves. Let's try a different answer. Let's try the negation. A plant cannot photosynthesize with no leaves. And again, it tries to synthesize an answer, a chain of reasoning. It finds one that passes the verification tests. And so now it's finally succeeded and returns that answer to the user. So this illustrates a nice interplay between the kind of fast answering that the answer module is doing and the kind of slow reasoning that the chain builder is doing in terms of trying to construct a chain of reasoning in support of an answer. So let me just mention some of the preliminary results on this. So we've tried this on a few data sets. On the common sense, and this is all 0 shots, by the way, tests on these data sets. On the new version of the common sense data sets, a state-of-the-art QA system, unified QA, really struggles with this data set, barely doing above random. When we run entailment writer on this, the score goes up to about 60%. And that happens because entailment writer will find answers in the original answers that it's unable to justify using its internal knowledge, and so corrects them. And so an example of that is this one. So originally, Unified QA thinks a sail could be made of paper. Entailment writer is unable to prove that, but it does find a proof for the negation. A sail cannot be made of paper because a sail requires strength, and paper does not have the required strength. So that's an illustration of one of its chains of reasoning it synthesized. We also tried this on this very different data set, a subset of the ethics data sets from Berkeley. Unified QA gets about 70% on this subset. Entailment writer gets about the same, so overall it's not significantly improving things, but it is able to pull out some of its latent knowledge to justify some of its answers. And so a nice example is this one. So entailment writer concludes that it's a bad thing if I tear down the birthday decorations for tomorrow, and the chain of reasoning it gives is, if I tear down the birthday decorations for tomorrow, then I'll disappoint the birthday boy or girl, and disappointing someone is a kind of bad thing. So this is a really nice explanation for one of these ethics questions. And then finally, we tested it on the ARC science questions. This is a collection that Unified QA does well on. And when we ran entailment writer on this, entailment writer actually does notably worse on this. And part of the reason from our failure analysis is sometimes bad chains of reasoning do still slip through the verification test that we're using. And so a bad example is this one. The question was, what's produced during the process of cellular respiration? The system thinks the answer is sugar, which is the wrong answer. And it gives the following chain of reasoning. Cellular respiration is a source of energy for the cell. Sugar is a kind of energy. And although this passes our entailment verification test, this is actually not a valid textual entailment conclusion from the facts that are given. So we still have work to do in terms of improving the ability of the system to recognize and distinguish good chains of reasoning. So I said there were 4 nice properties of entailment, right? I described 3 of them. The fourth one I want to mention is that as well as providing a question, we can also provide some declarative facts. And because of the way we've trained the model's strongly biased to then include those facts in its reasoning chain. So for example, if I ask the question, do plants require CO2 to make their own food? To continue with this example, but I also provide some additional information in the context, kind of hints of relevant information, like plants create food through photosynthesis. The system will use that extra information to bias both its answer and the reasoning chain that it generates. And here it generates a reasoning chain that includes that bit of information I've given it. And this provides a key avenue by which we might now interact with the system to influence and correct its behavior. And this takes me now to the last part of the talk, namely interaction and teachable systems. So the conjecture here, and I should say this last bit is very speculative at this point. If we can see faithful justifications for the system's answers, in other words, it's revealed some of the latent knowledge it has, which contributes to an answer, and if there's an error in the system's answer, we should be able to help debug the system through direct interaction. And so let me just show a quick dialogue to illustrate what I mean. So if I ask the following question to the system, can you pick up a penny with a magnet? And the system comes back with an answer. It says yes. In fact, this is the wrong answer. I had to actually go and try this out myself to convince myself this was wrong. I might ask, well, why do you think the answer is yes? And again, in the usual chain building approach, the system says, well, pennies are made of metal, metals are magnetic. Now there's actually an error in these facts here. So now I could come back and say, well, actually that's not correct. Not all metals are magnetic. Copper is not magnetic, and ask it to try again. And now if the system retries with this additional information provided in the context, it can attempt to answer the question and reattempt to form a chain of reasoning using this extra information. So it now says, no, pennies are made of copper, copper is not magnetic, and we get the right answer. So this is very nice. It shows how we might be able to debug a specific problem that comes up, but how might we make that new information persist for new problems? And so the picture we have is like this. We take entailment writer and we add a persistence memory of explicit facts, basically recording new information the user's provided and overrides to the system's latent knowledge inside it. And so I ask a question, can you pick up a penny with a magnet? It'll do some retrieval from its persistent memory. It'll combine the explicit retrieve facts with its latent knowledge to come up with an answer, maybe the incorrect one that I showed earlier. And at this point, the user can offer words of correction. As I showed before, not all metals are magnetic, copper is not magnetic. And these then get stored within that persistent memory. And now if I ask, can you pick up a penny with a magnet again, and with a good retrieval system that can find relevant information, it'll retrieve again relevant facts, including some of those that I provided. In the ideal case, we'll then get the corrected answer along with the corrected chain of reasoning. So this illustrates a kind of picture about how an explicit persistent memory of user interventions might be used to continuously improve the system through this kind of dialogue. So let me just finish with some reflections. So first of all, as I mentioned, we've had this a huge change in the view of what a knowledge base is, and there's a lot of evidence language models can be viewed as knowledge bases. But as I mentioned, and others have said, the way they use that knowledge is somewhat perplexing. They can make catastrophic mistakes. How do we move forward from this as a field? And I've shown how we can build a larger system consisting of actually several communicating processes. In this picture, I've simplified to two, that can provide reasoned answers to its questions. And just to recap, the answer generator is conjecturing answers to try and justify, and the proof generator is suggesting chains of reasoning to determine which of these answers to trust. And there is a kind of philosophical question about, does this output here really represent what the system actually did? And the answer to that depends a little bit on what you mean by the system. If we mean just the answer generator, then probably not. I mean, who knows what's going on inside? But if we think of the larger system, then the output does represent what that overall system did, namely constructing a reasoned answer from knowledge that the system believes. And then finally, as I speculated, if a system can verbalize some of its latent knowledge that it has that supports an answer, and the answer is wrong, we now have a handle on debugging it and correcting its misperceptions, which is a super exciting area and something we're pushing hard on. So if you'd like to know more, you can Google rule taker at AI2 or entailment bank AI2 to get more information. And I'll stop there. Thank you.
Okay. Thank you, Peter, for this very interesting talk. We have some questions, and again, a few minutes. So again, I'll jump right in. So Jason asks, in a previous talk, we heard about the difficulty language models have with negation. Is the intelligent verification model robust with respect to negation, and how did you get it to be robust with respect to that?
That's a good question. I don't have quantified numbers on this. It will handle negated questions, at least anecdotally. I showed one earlier about, from the common sense example, a sail cannot be made of paper, and so it'll handle that. My guess is it probably still has some brittleness with negation, so some of the earlier techniques on explicit methods for training on negation I think would be super useful here.
Okay, thanks. The next question is, do you think language models can be capable of reasoning over a question like, how many eyes does a foot have? And reply, no, feet do not have eyes, they have toes.
Right. So this is an example of a question with a false presupposition. Language models are known to be pretty brittle with this. If we were to ask a question like this to entailment writer, so I think language models are not robust to this kind of question. I think a language model is going to come up with an answer. If one of those answers is actually feet have 0 eyes, ideally this kind of proof generation, chain of reasoning generation method would identify that as the best answer to this question. But yes, this is definitely a known brittleness to language models at the moment.
Yeah, cool. Next question. Can you comment on how well training on synthetic data for reasoning can transfer to real-world reasoning tasks?
Yeah, this is a super good question as well. So we've done a lot of experiments thinking about with our rule taker system, exploring variants of wordings, and in fact, rule takers available on the web. We've kept a trace of all the various rules and facts that people tried when kicking the tires. If the real world text is reasonably close to the style of language that it was trained on, we end up with good transfer, and certainly paraphrasing rule taker and proof writer are reasonably robust to paraphrasing. When users get to more flowery language, I think that is a problem, and that's partly why we moved to entailment bank as an additional source of real text for training. I think in the ideal world, and this is something we're thinking about, is we would train on a mixture of synthetic and real data. I mean, the great thing about synthetic data is it's very cheap to produce, and clearly our system here would benefit from more of that and techniques to try and make synthetic data more real world.
Okay, we have time for one more, so I'll choose the non-anonymous one from Ron. Thank you for a very inspiring talk. I enjoyed it a lot. In order for such an entailment model to work, it sounds like it would need a big amount of data to be able to tell a true statement from false. Can you comment on how data hungry you envision such a model would be if it to be reliable?
Yeah, I mean, we're using the language model within it to tell whether a statement is true or false. So when the system asks itself, "Hey, is it true that that animals have 6 legs?" It's asking the answer generator, which is itself a pre-trained language model. So yes, that language model's absorbed most of the web to come up with that answer. Let me just add one other thing. Our verification system does sometimes still make mistakes. So it will sometimes believe its misperceptions. And so another addition that we're pushing hard on is to also try and verify some of these facts using external sources. So can we go, for instance, to a textbook or the web to find additional verification for the facts which it's generating to really be sure these are true. And of course, if we do that, we then end up with an additional nice property that we can then point to those external sources as provenance for the system's answers. So in the science case, for instance, being able to point to the appropriate part of a textbook that is justifying the system's answers.
Okay. I think that's all the time we have. Thank you again for an inspiring talk.
Thank you.
And I think we will have Peter also later in the chats and posters. And Samir should appear.
All right, thanks a lot, Jonathan. Yeah, so we're going to do spotlights now. And it's going to be 2-minute spotlights for about 5 papers. And then we'll switch to chats with Peter and Percy. There are lots of questions that they couldn't get to, so it'll be great to do that. And then we'll have a poster session after that. So the spotlight session will be the last one in this room. All right, so let's get started with the spotlights.
I'm Danilo Ribeiro, and I'll be briefly presenting our work called Combining Analogy with Language Models for Knowledge Extraction. The problem we're trying to solve here is knowledge-based completion. So we want to learn from text and populate an existing knowledge base with new facts. In our work, we target common nouns, such as dog or oxygen, instead of named entities. And the challenges are that we have to learn from an existing schema, so it's not open domain. We also have to learn using the cycle representation, so it's not simple triples. And we have to learn from very few examples. And our system is comprised of basically 2 modules. One is the analogical training. We show how this module is able to learn new facts from very few examples. And then the learn facts, we use a module for scoring the facts that uses a BERT classifier. And for the data, we use the knowledge base is the NextKB. That has around 66,000 facts, and we show how it has a long tail distribution where most of the relations actually have very few facts or examples. And the text corpus is simple English Wikipedia. And for baselines, we compare our system with 2 relation extraction systems using both CNN and BERT encoders, as well as text-to-text T5-based knowledge extraction.
Question the composition with dependency graphs. QDMR is the task of decomposing a question into a sequence of simple steps, a meaning representation that has been shown to be useful for question answering. While the common approaches are focused on sequence-to-sequence-based methods, we propose a new representation of such decomposition as a dependency graphs on top of the question tokens. We use this representation for creating a new evaluation metric that correlates better with human judgments compared to existing metrics. We explore two kinds of models. First, a non-autoregressive graph parser with slightly less performance in compared to the sequence-to-sequence model, but with 16 times faster inference time and a better sample complexity. Second, we provide a combined architecture where the sequence-to-sequence model is extended with dependency graph auxiliary loss through an additional graph head. The combined architecture achieves a better generalization on out-of-domain data and on QDMR structure with long sequences of computation steps. A manual error analysis also offers this architecture as a higher rate of correct predictions that were mistakenly classified as errors, leads to better overall performance. Thank you very much. See you on the session.
We present our paper on weakly supervised relation classification using language models. In the paper, we would like to send two messages. Firstly, we demonstrate that language models, such as BERT, can be used to generate noisy data for relation classification in a one-shot fashion. Secondly, we show that our two noise reduction mechanisms can mitigate the bad effect of the noisy annotated data. Okay, so firstly, how do we get weak supervision from language models? We follow the current one-shot fashion. Assuming that we have a set of predefined relation types and a single very simple example for each relation, such as Obama was born in the US for the relation type born in. We use a language model to find the best match of a given sentence against relation exemplars. The best match is then used as the noisy label. After annotating several raw sentences, we have a noisy dataset for training a relation classifier. To eliminate the bad effect of the annotation noise, we rely on two mechanisms. Firstly, we impose the inductive bias based on entity type pairs. This inductive bias can help model avoid unrealistic cases such as a place was born in another place. Secondly, we employ a noisy channel to help the model tolerate the annotation noise. We experiment on two datasets whose training labels are completely removed and replaced by noisy annotation. Our proposed model substantially outperforms the one-shot BERT, which is very similar to the one in Matching the Blanks by Soares et al.
Agnieszka Dobrowolska, and I'm here to present Neural Concept Formation in Knowledge Graphs, a joint work with Antonio Vergari and Pasquale Minervini. Concept formation in humans is believed to play a key role in allowing us to generalize quickly from few examples. In this work, we consider concept learning in knowledge graphs. Specifically, we analyze how one can learn concepts in knowledge graphs, and whether the newly learned concepts can be leveraged to improve predictive accuracy on downstream link prediction tasks. We begin by defining concept learning in knowledge graphs as performing unsupervised clustering of entities to learn new concepts and explicitly augmenting the knowledge graph with them. To achieve this, we propose two approaches. In Conforma, we first represent the entities using propositionalization, cluster them using a clustering algorithm such as k-means, and augment the knowledge graph with the new concept triples. In Conforme, the concept memberships and neural link predictor embeddings are learned jointly in an iterative expectation maximization scheme. We find that both approaches not only produce meaningful concepts, but also boost link prediction performance and improve generalization for rare predicates. There are several advantages to this formulation. Firstly, both conforma and conformer can be easily combined with any out-of-the-box neural link predictor. Moreover, explicit modeling of concepts can be used to alleviate the cold starts problem in sparse knowledge graphs, and allows for their embeddings to be used for various downstream tasks. For more information, please read our paper, join our poster session, or drop us an email. Thank you.
Hello everyone, I'm Keshav. I'll be presenting our work on multilingual fact linking. The task of fact linking aims to identify known facts that are present in a sentence. For example, given the sentence Delhi, the Indian capital, is known for its rich heritage, the following Wikidata facts are present in it: New Delhi, capital of India, and New Delhi, country India. We extend this to the multilingual setting where sentence and fact labels can be in different languages. For example, the sentence can be in Hindi and the fact labels can be present in English. This is an important setting because most of the fact labels are biased towards high-resource languages such as English and German, and are sparsely present in low-resource languages such as Hindi, Telugu, and other Indian languages. Solving this task will help us inject knowledge into multilingual language models, linking multilingual queries to shopping catalogs, and creating multilingual structured snippets. We released the IndicLink dataset to evaluate performance on this task for 6 Indian languages, where sentences are annotated with their corresponding Wikidata facts. We cover the following Indian languages in Hindi, Telugu, Tamil, Urdu, Gujarati, and Assamese. We present the RefCog model, which combines retrieval and constraint generation to predict the facts that are present in a sentence. We find that the model achieves scores in early 50s. This shows the challenging nature of the task and significant scope for future improvement. Thank you.
All right. Thanks, everyone. So next, we're going to have our the chats with the invited speakers and poster session. So please leave this room, make your way through the lobby and to the chats and poster session room. I will also encourage everyone to turn on their videos if they feel comfortable. Maybe you forgot to do that. I think it will give much nicer sort of cohesiveness to the conference and a much more friendly environment. So yeah, I'll see everyone in the chats and the poster session room. Thank you.